Welcome back to the series in which we get a lot of work done. So if you missed it last time we began this massive project more or less from scratch, we went all the way from the very beginning to having like a basic 2D multiplayer game that was running on a server and had multiple clients and everything. It was epic. And today we're gonna keep going. We're gonna go from 2D to 3D. Yes, entirely in this video. That's why it's so long. And I think this is particularly exciting because we're gonna start our Vulkan journey here today. So far for our 2D rendering, we've just been using functions that IMGUI provides us with. But today we're gonna learn all about Vulkan, we're gonna write some shaders, make some pipelines, and do some 3D rendering. As I mentioned last time, the end goal for this is to be a 3D ray traced game. However, because I don't want to alienate people who might not have ray tracing hardware or potentially fast enough ray tracing hardware, I also want this game to run and look pretty good in a normal rasterized rendering mode. I also think learning about that is probably going to be of interest to a lot of people. So this is a very important episode for that. I've also made a Discord channel for this series on my Discord server. So if you want to discuss this video or the last video, this project in general in more detail, then definitely check that out. As always, this video has chapters in the description below, so definitely use those to navigate around the video and have a look at what we're covering in this video. If you like what I'm doing, then definitely hit the like button and drop a comment with some feedback below. The best way to support this is patreon.com/thecherno, where you can also get access to my Hazel engine. Thanks for watching. I'll see you in the next video's intro. And so, let's begin our Vulkan journey. It all starts over here, docs.vulkan.org. I'm gonna quickly talk about some resources that I'll be using for this particular project. Me and Vulkan go way back, all the way to I think 2015, before it was officially released. I was working at EA on the mobile engine, and we were working with Kronos and various GPU vendors to get the beta Vulkan drivers working on Android. That was a complete disaster. Anyway, all of that behind me. Today, I'm going to be treating this as kind of like a, what would I do if I've never used Vulkan before? And also, disclaimer, I have forgotten a lot of the details because I don't spend every single day just working with Vulkan. So even though I did write Hazel's Vulkan renderer and all the Vulkan backend stuff, this is going to be a little bit of a walk down memory lane for me as well. Whilst I may reference Hazel's codebase a little bit if I get stuck, maybe, I'm just going to try and use the publicly accessible resources that everyone can use, such as this. So the Vulkan documentation, docs.vulkan.org, which I'll have linked in the description below as well, has a lot of information on all of the different things that make up Vulkan and how to use it. Now over here under education, there's also Vulkan samples. I think there's also Vulkan tutorial, but I'm not going to worry about any of that, of course. I had a very brief look at what was even in here just to see if I could use it as a basis for this project. Again, this is a live tutorial, so I'm trying not to do too much prep ahead of time so that you can naturally see the organic issues that might come up. Over here, there's this API usage examples, and we have, for example, Hello Triangle. And if you go to this particular page, you'll see that the source is available on this Vulkan samples repository. So today, I think I'm going to primarily use this file as a reference, as an example, to see if we can get a triangle rendering, first of all, and then we're going to try and move on to rendering an actual cube. Now, there is also a Hello Triangle with Vulkan 1.3 features example, and the biggest feature here that they're using is something called dynamic rendering. Dynamic rendering allows you to basically render using less code because you don't need to create render passes, frame buffers, and the pipeline creation is greatly simplified. Whilst dynamic rendering can actually simplify the code a lot, and on desktop GPUs, as far as I'm concerned, there are no performance penalties. It just runs as fast as if you verbosely write out everything yourself. I've decided to not use it for this project. I'm just going to do things like the original Vulkan way. If dynamic rendering is something you'd like to see, a tutorial, I guess, then let me know in the comment section below. Maybe we can have an episode or something where I convert this project to use dynamic rendering just to show how that works. So yes, this Hello Triangle example should give us everything I think we need. Now, the other point of reference is actually going to be already the application that we have. So the cubed application under Walnut has this application header file, which is going to either be headless or the GUI version. If we look at the GUI version, then this whole thing here was derived from IMGUI's example. And because this actually uses Vulkan specifically, you can see that this frame render function, for example, just is written in pure Vulkan code, and it calls IMGUI impl Vulkan render draw data. And if we look at this specific function and file, this file over here is under the IMGUI backends. This is not something I've written. This is just publicly available in the IMGUI repository. And this, you can see, uses Vulkan to render all of that IMGUI GUI UI. So this is also going to be an excellent point of reference. And in fact, a lot of the work has actually already been done for us, because obviously if we like launch this application, what we see here is all rendered using Vulkan. So we already have like a swap chain, a render pass, a pipeline. We've already got all of these concepts up and running. We might need to extend it and create some of our own, obviously, but we still already have that base point to start from, and that's going to be a huge help. As we work our way through this giant project, there's definitely more that you could be doing to subsidize your learning. And a great place to do that is brilliant.org, the sponsor of this video. Brilliant.org is an amazing website filled with lots and lots of really high quality courses on various STEM topics. If you found the programming part of our journey here a little bit too much and you want to start off with something a bit more simple and get the fundamentals locked in, then Brilliant's computer science courses are a really good place to do that, because they don't start off with a specific language. Instead, they teach you how to think like a programmer, and they help you build really good core skills. Their way of teaching is super visual, engaging, and interactive. Instead of just sitting back and watching videos, you'll be actively participating by like dragging these widgets, setting up the flow of your program, and you'll be quizzed along the way to make sure that you're actually learning and retaining this information. Math is another thing that's going to be super important for us for this project, and Brilliant's math courses are some of the best on the internet. They start all the way back at the very beginning, and they build into way more complicated things such as calculus. And again, with their beautiful visualizations and interactive content, it's honestly such a fun and effective way to learn. And the best thing is they have a 30-day free trial that you can use to check out all of the courses on their platform. Just go to brilliant.org/thejourno, link will be in the description below. If you do go on to like it, then that link will also get you 20% off a premium annual subscription. Huge thank you to brilliant.org, as always, for sponsoring this video. And now, let's get back to work. So that being said, let's talk a little bit about what it actually takes to render a triangle using Vulkan, because people of course love to joke about how complicated it is, and well, yes, it is complicated. At least to someone who more or less understands how Vulkan works, I wouldn't say it's complicated. I would just say it's very verbose. There's a lot of things that you have to set up that in an API such as OpenGL, you don't really have to. It's just done for you behind the scenes, and you can actually focus on rendering the specific triangle that we are talking about. In Vulkan though, you have to set up literally every little piece, but a lot of that is more or less boilerplate, meaning that like once you have that up and running and you've written it a very specific way, it's kind of there for you already, and then you can focus on creating what it is you're creating with potentially minimal tweaking of that boilerplate code, but usually you would parameterize it anyway so that you could reuse it. Again, this isn't really going to be like a very deep Vulkan tutorial, but I of course want to give you as much information as I can reasonably pack into this video so that if you have no experience or minimal experience, you're not completely lost and you actually learn something, which is why I prepared this diagram for you. So what this is an overview of everything we basically need to both render, which we'll have a look at in a minute, but primarily to create this thing called a pipeline. And specifically, I'm talking about a graphics pipeline here. The graphics pipeline, which you can find a lot of information about on the internet if you just look through various resources, is basically everything we need to go from some kind of data of what it is we're trying to draw to actual pixels written onto our screen. So in Vulkan, we actually need to create something called a graphics pipeline so that we can go through the pipeline and render what it is we're trying to render. And so what this pipeline is a description of how to do that rendering and what it is you're trying to do exactly as well. So if we have a look at what constitutes this pipeline, that is what we need to actually create a pipeline. We need potentially more than what I've drawn here, but this is kind of like the minimum. I'll cover the boring stuff first. So assembly/rasterization just defines our input assembly, so what it is we're actually providing in terms of like vertices, for example. And then by rasterization, I mean basically how those pixels are rendered. So like, are you blending them with like existing data inside the texture you're rendering to, stuff like that. Shaders are a very crucial part because they define what actually happens on the GPU when you render. So a shader is a GPU program that runs on the GPU that has a bunch of code that you've written that tells the GPU what exactly to do with that data that you're inputting, how to transform it into the output that you're looking for. There are lots of various different shader types. So the two most common ones, and the ones we'll be using here today, are the vertex shader and the fragment shader. The fragment shader is also known as a pixel shader, and we'll talk about those in more depth as we write some here today. Now, a render pass is a very crucial part of the pipeline. It kind of defines where you're rendering to. So if we follow this a little bit, you'll see that it kind of leads to a frame buffer. A frame buffer is basically the destination that we're rendering to. It's made up of images, could be one image, could be multiple images, and these images are really just textures that we want to actually write data to. Now they can come from the swap chain. That's why I've got this like as a dotted line, because our swap chain is basically our screen. So we have a bunch of swap chain images, they're alternating, and at the end of the day, this is what actually gets put onto our window that we have that is our game so that we can see something on the screen on our computer monitor. So what we can actually do is basically grab one of these images from the swap chain and use it as an image inside our frame buffer so that we can directly render pixels onto there. And that's what we'll do here today. Now, a render pass is kind of like the description of the attachments of a frame buffer without the actual frame buffer. So basically there's no data here because the actual image is inside the frame buffer, but the render pass has the necessary specification of like the layout of images basically and the format, stuff like that, so that our pipeline knows how to render. And then finally, this layout is just the layout of certain inputs basically into our pipeline. So if we want to use push constants, if we want to use uniform buffers, if we want to use storage buffers, if we want to use any of these resources and like descriptors for images that go into our pipeline, they have to be defined as part of this pipeline layout. So once we have a pipeline, we can move on to actual rendering. So how is it that we render things in Vulkan? Well, usually you would begin a render pass, which takes in both a render pass and a frame buffer. Because remember, the render pass is just the description of like the layout kind of it, whereas the frame buffer is the actual data. It's what we're rendering to. So that gets included here, because you may have noticed that this doesn't actually go anywhere. It gets used as part of actual rendering. Then we bind a pipeline, which defines how we actually render. Then if we need to, we would like bind buffers. So if we want to render a triangle and we're using like a vertex buffer or an index buffer, we would bind those over here. There's also like other things we would do here. So potentially if you want to use actual resources like storage buffers or textures, you would bind descriptor sets here as well. I've omitted that because we're not quite there yet. And then finally, you can actually draw. So you give a draw command and it will draw using basically the current state that you've bound onto a command buffer. And then you just end the render pass. So this is like a bit of an overview of Vulkan, I guess. Very, very brief. I'm not sure if I've missed anything. We'll see as we actually get into the code because I did this off the top of my head. But hopefully this gives you kind of the big picture of what it is we need to set up. So one of the crucial things and one of the hardest things I would say to set up are shaders. And the reason why is because it's not as simple as OpenGL really, where OpenGL just comes with like a shader compiler in the actual core OpenGL API. If we want to compile shaders from actual source code from text, we have to use something else, such as shader C or GLS Lang, which is something that we will potentially explore in the future. I didn't want to shove it into this video because I think that would make it way too long and complicated, especially because we can actually use an already available tool as part of the Vulkan SDK to compile those shaders offline. So instead of having our program compile it like on startup or something from source code, we can actually pass our source code into another program provided with the Vulkan SDK that will compile those shaders into SPIR-V binaries that we can then use as inputs into our program and into our graphics pipeline. But still, this part is a little bit complicated, so we'll see how we go with that. Everything else I think should be pretty reasonable, especially because I don't even think we'll need to create a render pass or frame buffer here because we already have those since we're rendering stuff to the screen in IMGUI using Vulkan. So my plan is just to kind of snatch these, but we're still going to have to create our own graphics pipeline since we're not just going to be rendering UI like IMGUI is. We have our own ideas for what we want to render, and we want to render triangles using our own shaders. So we will still have to create a pipeline. Okay, so let's have a little bit of a look through this IMGUI impl vulkan.cpp file because this has a whole bunch of stuff that I am interested in. And you can see, for example, that the way they handle shaders, they have shaders already written here. Here's some GLSL code, but they've compiled it into SPIR-V and they just have that SPIR-V bytecode over here as an array of uint32Ts. So this is basically what we'll be using that external program to actually produce from our GLSL source files. And in fact, if you look here at the comment that's again here inside this IMGUI file, you can actually see the command they run here. So they use this program called GLSL or GLS Lang validator, which is an executable included with Vulkan SDK, which I'll show you in a minute. They do -v, which means that it'll compile it into a SPIR-V binary. The output is just the output file name. I don't actually know what -x is. We'll look at that in a minute. So this is like the output, and then this is the input file. So we'll use this as well to produce something like this, but rather than pack it into an array inside C++, we'll probably just leave it as an external file since I think that's where we'll head in the future anyway. And if we follow where this is actually used, you can see there's a function here called create shader modules, which takes in that vertex shader and fragment shader SPIR-V bytecode over here into this VK shader module create info, and then runs a Vulkan function called VK create shader module to actually create these two shader modules, which are later going to be used inside our pipeline. Now, before we go any further, let me just talk about the actual Vulkan SDK that I keep mentioning. So if you just Google Vulkan SDK or you go to a link, which I will leave leave in the description below, you can get the latest Vulkan SDK. Now, there's actually a new one that's just come out 2 days ago as of me recording this video, Vulkan 1.4, which I believe has beta drivers for. So as far as I'm aware, Vulkan 1.4 is not like officially released. So I'm going to prefer using this version over here. Again, as of me recording this video, in the future, I'm sure this will change. And also feel free to, of course, try the latest version if you like. But if something doesn't work, just know that I will be using Vulkan 1.3.296.0. And this is the installer. You just download this. I will quickly point out as well that once you do download this, when you're installing it, something that I like to pick, which we may use in the future, is these shader toolchain debug symbols. If you don't have them, then you won't have the debug versions of shader compiler libraries, which we may use in the future. So if you want to know what my Vulkan SDK like installation configuration is, then this is it. So once you have the Vulkan SDK installed, you should be able to just go to your address bar, Control L, and then type in $Vulkan_ SDK and then $sign. So this is going to just take you to the environment variable Vulkan SDK. Inside your system environment variables, if we scroll down here, you can see that we have two that the Vulkan installer should have created, VK SDK path and Vulkan SDK. So this is very important because if you have multiple Vulkan SDK installations on your computer, just make sure that this is pointing to the right one. Why? Because inside our project over here, using the Walnut pre-make scripts that we basically based all of this off, don't know exactly where this is, but perhaps inside like this pre-make over here, you can see it's using library Vulkan, and there's also an include directory for Vulkan SDK. And if we have a look at where that's coming from, you can see it's using the actual environment variable Vulkan SDK, right? So this is the version of the Vulkan SDK we'll be using. Whatever your environment variable is set to locally on your computer, that's what it's actually going to use. So just make sure that that's all correct by just like trying to navigate to that Vulkan SDK environment variable and making sure that it's set. It's also possible to override environment variables in local shells. So just make sure that, I guess, you're not doing that if this isn't working. But anyway, this is the version of the Vulkan SDK we'll be using. And inside the bin directory is where that glslang validator.exe. I'll just call it glsl validator.exe. That's this program that we can use to compile shaders. And then if we go back a directory, there's also the lib, which includes like vulkan1.lib, which is not really like all of Vulkan itself because the real Vulkan is inside our GPU drivers, but this maps it to it. And then inside include as well are all of the header files that we'll be using over here inside our project. Now, let me quickly talk about this as well. So there's two versions of Vulkan really that are actually included inside the Vulkan SDK. There's vulkan.h and HPP. Now, HPP is like a C++ version of Vulkan, which does make some things a lot easier. And I guess you could say it makes more sense syntactically if you're working with C++. Now, I don't really use this. I don't have a hugely good reason to not use it. I guess I'm just used to like the vanilla Vulkan. But if you like the way that this looks, it's very, very easy, of course, to translate between the two, and it does slightly make your code be more concise, whereas like the original Vulkan is a little bit more verbose. So just know that that is an option to you. You can, in fact, use that if you want, and you can see it's included as part of the Vulkan SDK. So it's not like you have to download another library which has that mapping. It's all here. But we will be using just vulkan.h, which itself is not going to include much because it includes other files such as Vulkan core. And this is like where all of these functions are and all the structs and everything that you should probably familiarize yourself with. I mean, there's like 20,000 lines of code here, so that might take a while, but you can also use this, of course, as a reference to what we're doing here. Okay, I think I've covered basically all of the like documentational things that I wanted to talk about. Because Walnut already includes Vulkan, I think we probably also do as well. So I think we should just be able to start using it out of the box. We can always check by just trying to include vulkan/vulkan.h. And if we just hit Control F7 on this CPP file and it builds successfully, which you can see it has, that means that obviously that is part of our include path and it is in fact working. So we can literally just start writing Vulkan code here. Now, how am I going to do this though is an excellent question. I think the first thing we're going to try to do is probably have a look at where we would insert our rendering. So the goal for today is to render a triangle initially, and then a cube. Once we render the triangle, the cube should not give us any additional issues whatsoever. It's very, very easy to go from a triangle to a cube. Going to triangle though, that's going to be the hard part. So inside our application GUI file, we have a frame render function, which looks like, you know, a place where we render everything. If we go down to where it's called installed as part of our application run loop. So this is part of Walnut, and a lot of this is actually derived from an example IMGUI sample, I guess. So we start a new frame here for Vulkan, which is probably doesn't actually do much. We draw some actual IMGUI stuff. So this isn't Vulkan related at all. We render this stuff using IMGUI. So what IMGUI render does, by the way, is it doesn't actually do any rendering as far as like invoking a graphics API and actually rendering stuff. What it does is it creates its own internal draw list. So it basically organizes everything that we've tried to do in IMGUI into a list of drawing commands that we can then execute using any graphics API. So this is basically entirely on the CPU, just creating that list of render commands, if you will, that we then need to actually read and use a graphics API to render. And that's what frame render does. So inside frame render, you can see we have some Vulkan code. And then what we're doing over here is basically getting like the current frame. This is all like swap chain stuff that we don't really care too much about. And then over here, you can see we start running into some code that I talked about. VK command begin render pass. So all these functions with VK command are basically actual commands that we're giving the GPU to do within the context of a command buffer. So the first argument is always a command buffer, and that's just a command list, as DirectX 12 calls it. It's just a list of commands that we would like our GPU to run when we submit this command buffer. So what we're doing here is we're recording the command buffer in the sense that we're just giving it a list of commands to do. This line of code over here is where we actually begin the command buffer. So we're kind of opening it for the recording of commands. And then the first actual command we call, which begins with VK command, is this begin render pass, which is what I talked about over here in rendering. This is it. So the next thing, according to this, is we should be binding a pipeline. So let's see where that's happening. So over here we have VK command and render pass, right? So that's the end of it, which means that this part in the middle must be where we do all of the actual binding of the pipelines and rendering. So if we open that function up and we scroll down, there's a bunch of like sorting out what we're actually doing here, creating potentially vertex and index buffers, filling them with actual data. And then we do setup render state. So that will bind a pipeline, as you can see. So that's this step over here. Then we have bind vertex and index buffers, which is the next step over here. Then we do some other stuff such as setting the viewport, setting push constants, which is just pushing data onto our shaders so that we can read some data inside our shaders. So after this, we already have our pipeline set up, and then we can go through these command lists, these IMGUI command lists that we've created, set some more like rendering region stuff, and then bind the descriptor sets, which in this case probably just contain textures for like images or whatever we want to render. And finally, we do a VK command draw indexed, which is the actual draw call. So that's an overview of how IMGUI uses Vulkan to render all of the UI. And in fact, not just the UI, but those squares that we were rendering in the last video, that all gets rendered using this setup that we've just looked at. So then what we need to do is between this begin and end render pass, which is already rendering onto the swap chain images, we just need to be like, okay, well, before we draw our UI, let's draw some stuff here. This is probably the simplest way to actually set something like this up using what we've got. Because whilst we could create a brand new render pass and we could actually render that first and then composite like the UI on top of it, I don't really see a huge need to do that, at least not at the moment. In the future, we may move to a slightly more complex setup, because if we want to do things like post-processing, we're definitely going to need to have our own images in probably like an HDR format, so as 16-bit or 32-bit floats. We could even choose to do asynchronous like compute shader post-processing, meaning that while we're rendering the next frame using the graphics pipeline, we're doing the post-processing for the previous frame or for the current frame on our compute queue, which we can actually do simultaneously. So there's a lot of complexities here, and of course, I'm trying my best to not overcomplicate this, because we're not trying to make Hazel here or like a serious game engine. We're just trying to make a game here and learn a bunch of stuff along the way. So let's ignore that for now, and let's focus on this for today, because I think that's going to be more than enough work for today. Okay, so we know really that step one is going to be to just bind a pipeline, which is going to contain like our shaders and lots of other stuff as well. Then we need to bind these vertex and index buffers if we even choose to use them. And then we really just do our draw call. Like that's it. It's as easy as 1, 2, 3. Now, as I mentioned, there's this hello triangle sample as well inside the Vulkan samples. I've got the whole Vulkan samples repository checked out locally just to make this a little bit easier to deal with. And so you can see that this is a samples API hello triangle.cpp. So that's what I want to use. They have a function called init pipeline, which as far as I'm aware, we could probably just completely copy, because this just sets up a lot of kind of boilerplate functionality that we want. You can see this version is not using vulkan.hpp. There is a bunch of HPP samples, including HPP hello triangle, which uses that C++ Vulkan API, but the normal hello triangle just uses vanilla Vulkan, the C API, which is what we're using. So this is probably a bunch of code that I will copy in a minute. And you can see it also takes in these shader stages that we need. So we have two shaders over here, triangle.frag and triangle.vert. You can see this actually calls load shader module. And I think this does the compilation online, meaning it actually does the shader compilation inside this actual program, which we're not going to do. We're going to do it offline. But here are the two files. So this is located inside like shaders/triangle.vert and triangle.frag. These are like OpenGLES compatible shaders as well. So we could potentially use a newer version of the shading language since we don't really care about mobile compatibility and certainly not to that version. But you can see that their example doesn't actually even use vertex or index buffers, which is why if we have a look at the way they do their rendering inside render triangle, you can see they have a frame buffer, which they obtain from the swap chain. They also have a primary command buffer, which they obtain from the swap chain as well. Then they do begin command buffer. They provide like some clear values and a render pass begin info, which just begins the render pass and clears that frame buffer. Then we do a bind pipeline, a bunch of other stuff we don't really care too much about. And then we do command draw. So there's no binding of buffers. There's no binding of a vertex or an index buffer. They just do bind pipeline and they render straight away. But you can see the render command, first of all, isn't a draw indexed because there's no index buffer. It's just a draw, but they write 3 vertices over here with 1 instance. So that 3 vertices is important because inside the vertex shader, you can see they use this GL vertex ID, which since we're drawing 3 vertices will be 0, 1, or 2 as an index into this triangle positions array so that we can draw the relevant vertex position. And you can see a similar thing is happening here with colors as well. We could probably start out using this technique just so that we can get a triangle up on the screen faster without having to create vertex and index buffers, but I would still like to create those buffers later on because if we want to render a cube, that's going to be a lot of data that we have here. Not to mention we might want to take in 3D models as well, in which case, of course, we will need those buffers. So we'll see, kind of doing this on the fly. And then the fragment shader is super easy, just takes in that color that we output from the vertex shader and then draws it like for every pixel, right? So this is going to be interpolated. This will just give us like a, you know, that classic like multicolored triangle where it blends smoothly between like 3 different colors and we have like a gradient going on. So that is the deal with this. So I guess let's just start. I need to think about where I actually want to put all this code though. I guess I'll make a new folder called renderer. And then for now, I'm just going to keep this simple. Let's just make a renderer.cpp file and a renderer.h file. I'm not going to bother creating like 100 files or 100 classes for all this stuff. Let's do namespace cubed and then we'll have a class called renderer. Now, I'm making this a class because I do want to have like buffers and pipelines and I want to have some state in here. We're not going to talk about like complex renderer design. If that's something you want me to talk about in more detail, leave a comment below. I think I have discussed how Hazel's renderer works in the past. My ideal way usually to do this is we have a stateless renderer, which is just filled with render commands that we provide kind of all the context to when we call those relevant functions, but they still do a lot of the Vulkan heavy lifting. And then we have a stateful renderer, which I usually call the scene renderer, which actually contains all of these like renderer resources or renderer objects like pipelines, buffers, whatever else that it needs to actually convert a scene, that kind of input data, into an image output. But again, let's keep it simple for now because we're just trying to render something simple here today. So I'm going to include Vulkan. Vulkan is just going to be included everywhere. I'm not going to bother. One idea I did actually have, which I'll probably discuss later, is I did want to potentially build a render API agnostic system here and not really build one, but use an existing one such as NVRHI, which would basically enable us to build all of this stuff, but then have it run in Vulkan or DirectX 12 or even DirectX 11 potentially. I mean, the ray tracing stuff won't work with DirectX 11, but the rasterization stuff will. So if that's something potentially that you think I should do, also leave a comment below. Just give me feedback during this whole thing because this is a huge project, really. I'm trying my best here and I don't know what you guys would prefer. So as always, please let me know. Okay, so we have Vulkan over here. So this is really where we're gonna have our pipeline, right? So I think it's just gonna be probably VK graphics pipe or graphics pipe. I think it's just VK pipeline. Okay, so we're gonna have our graphics pipeline, as I'll call it. We'll set it to null pointer. Now, VK pipeline, all of these like Vulkan things, you can see they're non-dispatchable handles, which really just mean that they are pointers. They could be UN64Ts if we don't have 64-bit pointers on. So if we're building for 32-bit, I guess they will be that. But in most cases, you can see that they are kind of a pointer instance of like this object struct, where object is obviously the type that we're using. So for VK pipeline, there would actually actually be a struct called like VK pipeline T, and this would be a pointer of that struct. So that's why usually I set these just to null pointer to initialize them, because of course you don't want them to just be random memory. That way you can see if you're trying to use a pipeline that you haven't actually created yet, right? So if you're trying to bind pipeline and it's null, obviously, you know, that's not valid. You must have forgotten to create it or something, as opposed to just like it not working because of some random memory that you're trying to pass in, or like a random handle value. So this is ultimately what we're going to do. So maybe let's just have like an init function that will probably like create this. We can have a shutdown as well, which will shut everything down. And then I think I'll just have a function called like render or something, which we will fill in later. So going to the CPP file, let's include renderer.h. We'll do namespace cubed over here. And then I'm just going to create quickly using Visual Assist here, the function definitions. Okay, cool. So in init, let's create our pipeline. So going over here to our Vulkan samples, which I forgot I actually have open over here, there's a function called like init pipeline, which I think I will probably make an actual function for, just so that it's clearly separated. And then we are just going to copy and paste all of this, and then we're going to talk about it, because this also does like some shader stuff. Okay, cool. So there is this VK check thing, which I'm a little bit interested in, because that's just going to have some like error checking for us. So if I search for that, should be something like define VK check, Vulkan tools maybe. You can see what it's doing over here. Here we go, inside framework common, we've got it. It does just throw a runtime error. I don't know if I necessarily want to do that. Oh, and then VKB2 string would be good as well, because that's going to convert the Vulkan like enum value to an actual string that we can read. So we'll probably grab that as well. Let's make a new file here called like vulkanutils.h, and then we'll just put that into here. We could actually just call it like vulkan.h, I think, and then that would be kind of like our vulkan.h. So that would include the actual vulkan.h header as well. That way we can just include our one, and it's got everything, including our utilities and stuff. Now VKB2 string, that's going to be fun to find. Okay, so I found it over here. So we have like a whole bunch of stringified enum values here. This is they've got like a define over here, like inline inside the function, which they then undef. That's pretty funny, but whatever, I'll grab it anyway. And then we're just going to pop this up here. Let's also, I guess, include string, that here. Okay, and I'm hoping this will work. Let's put this in like, I think it was originally in like this VKB namespace. So let's put that in there, because I don't want that to be in a global namespace anyway. And in fact, I probably want this to be inside a CPP file. So let's also make a vulkan.cpp. We'll include vulkan.h. We'll copy basically all of this. And then I'll go back to the header file and just leave the function declaration without the definition. And that should be okay. So now hopefully VK check works. We're going to need to make sure the rest of this works though as well. So we definitely need the device, the actual Vulkan device, to run any Vulkan functions really. And then we're outputting this pipeline layout into this variable over here. So as well as the pipeline, let's create something called a pipeline layout. So we'll have M pipeline layout over here, which I'll set here. And then as far as the device goes, yeah, we need to pull that out of IMGUI. So if we have a look at how IMGUI uses this device and everything, I'm pretty sure it's just inside this IMGUI impl Vulkan get backend data. And then here we'll probably have the actual VK device. Might not even be in here, init info. It's probably in here. Yeah, okay. Okay, so here is this get backend data function, which you can see just makes sure that we actually have a current context. And if so, it gives us this cast into IMGUI impl Vulkan data, because of course it could be any rendering API, but in this case it's Vulkan. Otherwise we return null. So this isn't actually exposed. You can see it's a static function, so it's internal to the CPP file. We are still gonna have to use it though, so I'm probably just gonna copy it, and I think I'll put it into this header file over here, maybe in a namespace called cubed. I'll copy this and put it into a cubed namespace in the CPP file. So we're actually doing this stuff in the CPP file. Just probably call this get Vulkan backend data. I don't know if we need like all of the backend data though, because another thing we could do is we could just use it to access the actual stuff we need, like the device, but whatever, we'll just leave it like this. I think that's fine. So this is implemented inside, oh, this is actually in the CPP file. Great. Okay, so we might actually have to modify this. I thought at least the struct would be kind of inside the header file, but it looks like, oh, it is inside the header file. Oh, the init info is. So the backend data isn't, but the init info is. Okay, well, that's fine. We'll just change this to be the init info, and then we'll do include IMGUI. I think it's like, to actually find where this is. Oh, it's just in backends, yeah. So this should be just be in backends and then Vulkan, right? So we've got our init info, which will call get Vulkan backend data, which we'll rename to get Vulkan init info. Maybe just Vulkan info. Then let me just grab this and replace this here. So now that we get this, thing is we don't exactly have access to this though. Is there really no way to get init info without that? So there's get backend data, but there's no get Vulkan init info. I mean, the best thing to do would probably be to just modify this file and just give it a function that returns this init info, and then we'd be done. But if we really didn't want to do that, one thing we can do is this struct, even though we don't have access to like the layout of this struct, right? Because it's inside a CPP file, we know that the very first thing inside it is actually this init info, which is in fact public and what we're looking for. So what we can actually do is just cast this directly into an init info. Because whilst that's going to obviously ignore the rest of this and just be like, oh yeah, you're just dealing with that, that's exactly what we want to deal with. And because these are just like pod struct types, there really won't be any issue. And then we have access to everything we need. So yeah, it's a little bit dodgy, but it definitely works, I think. We'll see if this ever ends up giving us any issues at all. All right, so now we have get Vulkan info and we should be able to access our device. So back inside our renderer, we should be able to do vk device equals, what is it? Get Vulkan info and then device, just like that. And then that device can go into here. And then hopefully this will work. SCD has not the runtime error thing. Okay, yeah, do we really want to throw an error? Probably not. Let's just do like, I don't know what the logging, I forgot what the logging situation is. Let's just do SCDC out. Let's just do Vulkan error. Can do that. So that should be good now, maybe. Let's just include IO stream and then are we good now? Expected a semicolon. Where did it expect a semicolon? That is a bit bizarre. We might come back to that. Okay, so then we have this array. So what's wrong with this? I think we just need to include array. Okay, and then we got this, so 2u32t, which is just casting it to a uint32t. I really don't know why that has to be so difficult to use a function for that. By the way, you're gonna see me use like C style casts. That's just who I am. Sorry. You can use C++ style casts, you know? So like the proper way to do this, I guess, would be static cast uint32t. I just think it takes up more space and you know, you have to wrap everything in parentheses as well. I just don't really see the value of it, to be honest. Searching for casts is not something I think I've ever done in my entire career. So we're just gonna leave it like this. Okay, so now really all that remains is, let's just cast these as well here, is, okay, so we need the render pass, which we actually have, right? So I think inside here, inside get Vulkan info, we also have like the render pass. Oh, see, that's in the backend data. See, this is annoying, right? Because yeah, it's in here. So I don't know if we're going to, oh, well, okay, but hang on. The thing is, we probably, like, render pass is probably pretty much the only thing we actually need from here. So what we could do is, instead of like trying to open this up, because I'm clearly avoiding that, if we go back to application where we're trying to render this, in this situation, we obviously have access to the render pass because we're beginning the render pass, right? It's inside here. In fact, this is in something else. This is inside the window data. And this might be important because since we have multiple viewports, we might also have multiple render passes set up for them because they'll have their own independent swap chains. If we have, and by viewports, I mean like you can drag windows off in this branch. It's like the docking branch of IMGUI, which has that kind of multi-window support, and so because of that, each window is going to have its own swap chain, thus its own frame buffers and render passes. I mean, it might not necessarily have its own render pass, I think, because the frame buffers are going to be different, but render passes might not be, but it might. So in other words, we can use it from the window data like this. So that means that when we create this stuff, we can either get the render pass from whatever context we're rendering from, but you can see that's also dependent on the current frame here, which probably shouldn't be like exactly true. Like we definitely shouldn't have multiple render passes across different frames. So I wonder how this like gets set up. So you can see, yeah, there's just like this gmain window data, which we could use, and that's stored inside application GUI. And I guess we can give it that render pass. When we do come to frame render though, we're going to get the context of the window we're rendering to and also this draw data. But I guess we're just interested in, so that's interesting actually. That's one thing I didn't consider. The fact that this frame render, because it does take in the parameters of the current window and draw data list, it might actually, well, I expect it's going to be called per window. So we've got our main window, but then we might have like additional windows that are not part of the main window. So in other words, this function is going to be called 3 times. And we obviously don't want to render our triangle like in every window, right? We want to just render it in the main one. So if we have a look at where this is actually called though, you can see that initially it is called with just main draw data, right? And with WD, which in this case, is set to our main window data. So I think it's probably safe to just create our renderer, let's just say over here, and probably pass in the main window's render pass. So let's include, oh wait, this is inside Walnut. Oh, I totally forgot this is inside Walnut, which I don't know if we want to modify that or not. I think it's probably fine too. Yeah, in fact, I was going to have an episode on like application architecture, so we can talk about that then. Let's just get this up and running. So we'll say include renderer, but this is inside cubed though, so that might not actually work. So here's what we, I think, can do. If we have a look at Walnut layers, at the moment they don't have like a render function. They've got on update, they've got on UI render, but they don't have just a normal on render where we might want to do like 3D graphics rendering, for example. So let's add that into Walnut's layers, because then what I'm going to do, what I want to be able to do here is inside frame render in a very specific position, like over here, I can actually go through like the layers like this and call on render. So this function is static though, so we might need to just have it take in our application instance. So we'll do Walnut application, then we can do application. So layer stack's going to be private, so I think we can just do get layer stack, and then we can just add that over here. So here is our layer stack. Let's make it a const vector, sure. Get layer stack. And then we should be able to just call on render here. So we've got that context here if we would like it. We can pass some additional information into here if we want to. And that way we can go back to our client layer over here and actually have a function called on render, which we override, and we know that happens in the right place, and we've got that context if we want it. So then we'll store our renderer inside client layer, which is already better, I guess. I mean, we're inside this module anyway. That's where we created the renderer, so that's probably important. I don't know if we want to maybe bring some of this renderer to Walnut. See, like the thing is, I'm not trying to, like, I don't want to make a game engine here necessarily, right? So I think keeping this game side or game specific might probably just be better, and it'll certainly be easier. So yeah, we'll see how we go. So this is kind of now inside here, really. So I'm going to move my comment over here. And so the one thing that I really still need access to is going to be, let's just make a renderer here. In order to call renderer init, which I can do, for example, inside on attach, I still need access to that render pass, which I don't really have. So the application obviously does, and it's inside this main window. I mean, I could probably get it, to be fair, because it's inside the main window draw data, right? So this G main window data, which is obviously globally accessible, but it's actually inside application GUI. So I could get it, but I'll probably have to provide something for that. So let's try that. We'll see if it ends up working the way I want it to, but I mean, this is a defined where inside here, inside import Vulkan. That's probably okay. Down the bottom here, let's add a static function over here, get main window data, and we'll implement it down here. I'll make this a pointer, yeah, and then we'll just return that. So now inside our client layer, well, inside anywhere really, including the renderer, because this is going to call init pipeline, we should be able to do application get main window data. So this will be Walnut application get main window data. We'll include Walnut application, and then inside here we should be able to get the render pass. So it's a lot of work to get the render pass. But we now have the main kind of render pass for our main window. So that's like the convoluted way to go through everything to actually retrieve that render pass for a window. Again, to me, this like still makes sense. It might sound like a bit of a hack or a workaround. It's not really, because this is specifically pertaining to the main Windows render pass that is in fact created for us. So if we want access to that existing kind of pipeline and render pass and whatever else from the main window, then that is a perfectly reasonable way, I think, to get it. Again, in more advanced custom applications, you'd probably create your own render pass anyway, which means none of this would actually be a thing. But then again, you also wouldn't really be rendering in the middle of a render pass like we are by calling this on render function that I put in. So we'll see how we play with this design as it evolves. But again, the goal for today is just to get that triangle and a cube up and running. So renderer init should be fine to now run over here, because obviously it can hopefully retrieve this. I'm gonna have to like put a breakpoint here and make sure that the render pass has already been created by the time we run this. It should have, because we're inside the onAttach function, right? We're not in the client constructor, the client layer constructor. We're inside onAttach, so it should already be created, I think, and ready to go. Okay, this is still upset if that's a real error. Let's go down here. So load shader modules is this like next thing that we really need to load. this is going to be probably fairly easy. We'll have to look at what it actually does though, because remember the version there compiles it, but we don't really need to compile it. We just need to actually load like the bytes from disk and then create like a VK shader module out of that. So maybe I'll have a function over here called load shaders. We'll do that, first probably. And then maybe I'll have like a load shader, probably from a file path. And then I don't know, like, do we specify what kind of shader it is? Maybe like we could have like VK shader stage flags. So this just lets us specify like what shader stage that actually is. So here are the actual shader stages. This is inside Vulkan core.h. So we could specify, for example, that we want a vertex shader and a fragment shader and then pass in certain files for it. We could also detect it like by extension or whatever. I think I'm not gonna worry about that too much. I might just put the shader stage here first, and then we'll do the actual path. And the idea with load shader is it'll kind of create like a shader module for us. And so to do that, if we do VK create shader module, you can see it needs a VK shader module create info. Usually what I do with these, so this is one of the reasons why the CPP version, I guess, of Vulkan is better. Every single struct that you create like this, like these create info structs inside Vulkan, the very first parameter here, the very first variable is a VK structure type, which is just the type of structure it is. So there's all these like structure types. And so the idea is you just need to pass that in as like the first thing. And that's just a way to verify that you're actually dealing with like the right kind of data. Now inside vulkan.hpp, that's handled for you actually, so that's kind of nice. But here we'll have to do VK structure type and then shader module create info. It's literally the exact name of this, but just with VK structure type as like a prefix. So because that's required, I like to just create it on one line like this. The alternative is obviously just to create the struct like that and then set the structure type to that. Now obviously this takes up 2 lines of code, whereas this takes up 1, so I prefer this way. And then you can see inside here, we just need to set the code size. Any flags, we have the actual code, which is just basically a uint32t pointer to the data. This next will be null, and then we've already got the structure type, right? So it's just like really, I don't even know what flags are in here. And you can see, by the way, this doesn't actually have a shader stage, so we might not need that. But if we look at the flags, so if we have a look at the Vulkan spec, so the VK shader module create info, you can see that flags is reserved for future use. So they're not actually using flags here at all. Turns out it's probably why I was not aware of what it was even for. Okay, so that being said then, the two important things here are the actual like code and the code size, right? So these are 2 things that we need to set. And this of course is just code size because P stands for pointer. Okay, so to actually load these files, I guess we'll just use, so let's include fstream. Could use the C-style API. I quite like the C-style API, but let's just try and use the C++ one. So input file stream, and then we'll have the actual file. So we'll take in path and then std like iOS, I think binary, treat it in binary mode. And then let's just make sure we close the stream at the end. So here, we should probably figure out, well, if, okay, let's do if stream is open. There's also stream.good. I never remember what to do. So if it doesn't open, let's just return like null. Right, because remember we're returning a VK shader module. Otherwise, we need to find out how big it is. So I think if we do seek G, so if we go to the end, okay, so here we go. A little bit of Googling. std iOS base, and then we can do end to seek to the end of the file. Is this still like what we need to do? It's been so long since I wrote manual kind of code like this. So obviously engines and whatever else would already have this long written, and then like tell G, I think, to just tell me where I am, and that gives me like a stream position or something from memory. So this kind of gives me the size of the file really, and then I go back to the beginning so I can start reading it. That means I can create my vector. Now this thing actually wants like a pointer of uint32t's, which we could try and directly read this as uint32t. It's not going to matter at the end of the day, right? Because we're just going to give it like a pointer, and we can cast that to any type because the data is all going to be there. It's just a memory buffer. What does matter though is I think code size though I think is in bytes. Actually, do I still have that up? Yeah, okay. So code size, yeah, is in bytes. So that's important because that means that if we do have it as a uint32t, it's not actually going to be the size of the vector. It's going to be the size of the vector times 4. So I don't really know. I think what I'm going to do is probably just read it in as uint8t, so it actually is bytes. And that way we can just like create a buffer over here like this and then make it be size. Then we do stream.read. So we're going to read into buffer.data. I guess this one's a char, so we could just make it a char. That way we don't have to do any casting, and then the count will be size. So there we go. We've read all the bytes in, hopefully. We've got them inside buffer. That's kind of done. We can close the stream. This will get destroyed at the end of the stack, at the end of the function. And then now we can just set code to be buffer.data, which we'll need to cast into a uint32t pointer. And then we'll set the code size to just be buffer.size. And this will probably have to cast. Oh, that's a size T. Okay, that's done. And that I think is it. So now we can do create shader module. We need that device again, which we can grab like this. Our create info is over here, no allocator, and then we get an output shader module. So VK shader module, we'll just say results, and there we go. We should wrap this inside a VK check, probably. Does this return a VK result? It sure does. And I think we're good. I really want to figure out this thing though. Expected a semicolon. What is wrong with my macro? Oh, I have an extra parenthesis. Yeah, there we go. Cool. Okay, so finally we have a way to load shaders. So let's do VK shader module. And I guess, yeah, we really don't need the shader stage at this point in time. So I was wrong about that. Let's just do vert shader. We'll do load shader. We'll just put into like shaders basic.vert or whatever and basic.frag. So that's what we'll output our shaders to, I guess. Maybe the raw ones will just be .glsl.vert or something. Or should we do like .vert.spurv? I don't know. We'll see. But either way, we have both of these shaders. So I think, well, actually, since we did this load shader function, we could probably just do it as part of the pipeline. So we could just load them here. And then obviously we just need to pass in the shader module. So this is just, well, yeah, or actually even how they were doing it to make it even better, even like less code. So let's grab this. Down here we go. So yeah, main will be the entry point, at least for these shaders. Fragment and vertex bits, so the stages are set up. We need the render pass, which we obviously have. The pipeline layout is something we just created here as well. Create graphics pipelines. So sure, we got our pipe there, and then we're gonna put that into graphics pipeline. Device is just device, and then we'll destroy the shader modules, I guess, because we don't need them anymore. A little bit weird, I guess, that we're creating the shader modules here and then destroying them here. A bit of like some asymmetry here, but whatever. That should be good. So we got one error up here with load shader, didn't I? VK shader module. That looks pretty good. Oh, const part. No, that looks good. Let's just try and build this, see what happens. Okay, file system. Yeah, we didn't include file system. So we'll include file system. All right, cool. So we're compiling. See? How hard is this? Not very. Am I right? No guarantee any of this works though yet. So let's maybe write some shaders now. I guess I can, well, we were basing it off of this, weren't we? Okay, so we're going to use this as a base, and we're going to potentially tweak it a little bit. I mean, it's basically everything we need. I'm just not going to use specifically version 320, and in the future, we will probably switch from using these constant arrays over here to actually using vertex buffers and index buffers, but it's a really good start. So what I might do is let's just reveal this in File Explorer. I'll grab both of these shaders, and then I think I've got over here in Cubed. So Cubed client, let's make an assets directory. Let's make a shaders directory, and then I'm just going to put this in here. Now I think we called it like basic.vert, basic.frag. Let's have a look at what we're actually trying to load over here inside our renderer. So let's do assets, shaders, and then, okay, basic.vert.spurv, right? That's right. I forgot that these are actually going to have to be in SPURV here. So let's maybe do like a basic.frag.glsl. I'm going to open up these in Visual Studio just by dragging them in here. We can get rid of the precision and all of this stuff. The version I think we'll stick with is probably like 460 core. This is the fragment shader. So we've got our input color and our output color. I guess we can probably keep that as well. Let's do the same to the vertex shader as well. So we'll just do 460 core, get rid of the precision. And then, yeah, you can see we're just writing out our GL position to be at whatever our triangle position is, and 0.5 for the Z and 1.0 for the W component. Yeah, so this will just be assuming that our clip space is going to be -1 to 1, which it will be. This will draw a triangle roughly around this size inside our viewport. And I might talk a little bit more deeply about how the shader works a little bit later. It's pretty simple though. Let's try and compile this now. So if I go to our shaders directory, let me first of all see if GLSlang validator is a thing here. Okay, it is. That must mean that that bin directory inside the Vulkan SDK is part of my path, which is great because it means that I can just do -v for SPURV. And by the way, you can see there's all like these target environments. For example, we could set this to be like Vulkan 1.3 or a particular version of SPURV if we wanted to. If you scroll up here, you can also see the usage. So we have our options over here and then the actual file that we want. In terms of our options, they're all listed here. So -v will create a SPURV binary of a particular version under Vulkan semantics, which is what we want. There's like, you know, certain defaults for shader versions. And then I think -o is the output that we're looking for. So a lowercase -o save binary to file. So we should just be able to do GLSL validator -v. The output we can set to like basic.vert.spurv. And then the input is going to be basic.vert.glsl. And that looks like it's done. Let's do the same thing now for the frag. And if we have a look at the directory, we should now have 2 SPIR-V objects over here ready to go. Now, because it's going to be annoying, obviously, to type this in every single time, what we can do is we can just make a script that runs this shader compilation thing. So if I just create a new file here called compile.bat, we'll just make a little batch file. All I have to do is copy this, and then we can do @echo_off, call, and then that for both vert and frag. And then we can maybe do a pause as well. We're on Windows here. Obviously, it's a batch file, so that will just, if we run this, it'll just basically compile all of this, and then it will pause to show us any errors that we have. Speaking of errors, if I do actually make an error, so let's just say I forget this like comma over here, if I call compile, you can see it should tell us that there's a syntax error on line 8, and we can hopefully fix that. So we've basically got like a little shader compilation pipeline going on. As I mentioned, in the future, I typically in my applications like to get the actual application to have the capability to compile shaders. Then again, I am used to making game engines where that does make a lot of sense, since a lot of the time as part of the game development journey, you are authoring shaders. So therefore that pipeline and that workflow makes a lot of sense. Might not make as much sense for a game, but either way, I think it's nice to be able to have that functionality. That way we can easily just like edit our shaders and then reload them in the game without having to compile them like through an external program. Although that being said, that wouldn't be very hard to set up either, just to compile through an external program and then reload those SPIR-V binaries. So either way, I don't know. Let me know if you think it kind of fits the context of this series, or if that's kind of an unnecessary complexity that we can just avoid. Okay, so we've got the shaders either way. One thing that I might do is I might just put them into a bin directory, right? So at the moment, compile, if we go back to compile, we'll just maybe make them go into that bin directory. Let me just delete them from here and make sure that that works. That way we have our binaries packed away, and then the source code is obviously in here. Okay, cool. So that's very easy to get running. So let's do shaders bin. We'll load those SPIR-Vs, and that's pretty much it, I think. Let me just have a quick look through this. So load shaders, I'll get rid of since we didn't end up needing that. We just have init pipeline and load shader, which obviously does what we expect it to. I might also just grab the load shader function and put it underneath init pipeline, just doing some organization, but otherwise that looks pretty good. So now for rendering, how should we have a look at rendering? I think if we go to maybe the hello triangle example, we've obviously done this part. So maybe let's just have a look at what actually happens in the rendering section. So that's over here. So yeah, we set the viewport and the scissor, which we might talk about in a minute. And then the begin render pass is pretty basic. So we just bind the pipeline, we set the viewport and scissor, and then we draw. So actually, let's just grab this code, and then we'll come over here into render, and I'll paste it in. So we do actually need a command buffer, which I didn't really think about. So we'll have a look at how we can retrieve that a little bit later. Maybe let's have a look at that now, actually. So application GUI, and what is it? Frame render. So we have a command buffer that we start over here. And this command buffer, you can see, comes from the frame data. And this actually is important because this is a per frame thing, right? So you can see that we actually look at the frame index, and then we get the relevant command buffer. We shouldn't have a render pass per frame. That doesn't really make much sense, but we should have a separate command buffer for each frame index, because if we have multiple swap chain images, we have multiple frames in flight, it makes sense for us to be recording different command buffers, and there's not necessarily just a single command buffer for us to write to. So what all of that means is just that when we do this code over here, we need that context of the current frame. We can't just get some kind of globally constant command buffer that we need to actually write commands into. It needs to be this one specifically. So we have a few options here. We could just grab this VK command buffer and actually pass it over here into this function as a parameter. So that would look something like this. And it makes sense because the rendering commands contextually are being written into this command buffer. I think that's probably a decent way to do it. It does mean that obviously we are tying all of this to Vulkan specifically, because we're going to introduce VK command buffer being a parameter in here. The other alternative is just to simply store it inside application as like an active command buffer, and then make sure that we always use it within the context of an active command buffer. So for example, when we actually do begin command buffer, we could set an active command buffer, and then when we do end command buffer over here, we can set that back to null. And that way we'll make sure that we are in fact using the currently active command buffer. That's probably a cleaner way to do this, just because we don't have to pass VK command buffer everywhere and also have that Vulkan include going. So I think I'll just do that, and we can call this like the main application command buffer, or the main window like swap chain command buffer, whatever you want to call it. So over here, I'll just type in static VK command buffer, get active command buffer. And then what I'll do is I'll have that return this S active command buffer. And so over here at the bottom, I might just have this VK command buffer, which is our active command buffer, which we can set to null. And then if we go into our CPP file, of course, then inside frame render, when we begin our command buffer, we can say that this fd command buffer is now our active command buffer. And then when we end it, I'm just going to set that to null. So this is basically like some transient command buffer that we have that we really should only use in client code within this section here. Otherwise, it'll be null. Obviously, if we start introducing multiple threads to this, it might also lead to some issues. But typically, especially with a setup like this, where we have a command buffer that is responsible for actually rendering our swap chain, that would be like obviously centralized in one place. And if we wanted to multi-thread some kind of rendering, we would just branch that off and create our own command buffers for that multi-threaded code that would run on other threads. So overall, I don't think this is too bad of a design or anything like that. Let's try and build this because I am getting some errors here. Okay, so we've got some kind of syntax error over here. I think it might be this not being included. So let's do backends that will include the Vulkan backend over here. Try and build that again. Okay, that's better. Illegal reference to non-static. So we forgot to mark that as static, didn't we? Let's make this inline static. Control F7 on the CPP file. Okay, so S active command buffer undeclared identifier. Oh yes, okay. That's why I wanted to set it up differently. So we obviously don't have access to this specifically. There's a couple things we could do. It is static, so you would think that something like this might actually work, but it won't because this is private static. So what I would do instead is actually at the top of this file, we already have a whole bunch of stuff going on here. We've got like these globals that I didn't create. They're just IMGUI things. And then we've got a couple of things here that we created for Walnut. So what I might do is I'll put that into here, into the CPP file, and it's not going to be part of the class at all. So if we get rid of the inline and we copy and paste that into here, we've got an active command buffer in here, and there's no mention of it whatsoever within this class. Now we still have a function that needs to return it, but that's fine because we can just implement that function in the CPP file, which means that it obviously can see that active command buffer, which is just at the top of the file, right? And static just locks it to this file, so there's not really a global variable. Let's try and build that. Okay, and then finally frame render does not take 2 arguments. I wonder what happened here. Oh, we tried to add application to this, didn't we? Did we end up using that? Yes, we still have to use application get layer stack. Totally forgot about that. I guess we've never tried to compile this file before. So we can just include this. Like that. All right, let's try and build this file and hopefully we should be good to go. So now back in our renderer, we should be able to call application get active command buffer. This is obviously going to be inside Walnut application. That will give us a VK command buffer, which I'll just call command buffer. And that is what we'll take into here. So I'll just copy and paste that in here. Okay, so we obviously need the pipeline, but that's the pipeline that we created within here. So we can just pass in mgraphics pipeline. Then we have the swap chain dimensions, which is going to be important for the viewport. So let me quickly explain this viewport and scissor thing. So viewport just refers to the kind of region that we're rendering to. So within the actual texture, that is the underlying data of the frame buffer of the render pass that we're trying to render these pixels to, we have like a viewport, literally like a little window into that texture that we're allowed to render into. And of course, if we define something here that is some subset of like whatever is in there, like some subregion, then anything outside of that won't get rendered. It will get clipped. So this just allows us to clip our rendering to a certain region. Now, scissor is kind of similar to that, except scissor is used specifically for being able to cut off certain areas. That's why it's called scissor. So anything outside of the scissor region just gets sliced off. And the reason why this is important is because you might have, especially in UI, you might have some text being rendered, but like for example, for a sub window inside this window, and you might want certain areas of it to be cut off, because if this is like a sub window within our larger window, obviously this is all part of one frame buffer. The frame buffer is the whole size. So therefore there's no real way to just get rid of this text since it's not actually outside the viewport. It's not outside like the render area, but it is outside of a render area that we've defined for this specific draw call potentially, or for this specific render pass. So that's what scissor allows us to do. And if we have a look at these structs as well, you can see that viewport defines an X and a Y as well as a width and height. It's just not set here. And the scissor extent also has an offset and an actual extent that we can set. Now in this case, we're just trying to render to the whole screen area. We don't really care. And so because of that, you can see they're just set to the swap chain dimensions, which is our entire application window dimensions. Now, another note here that I want to mention is you can see that there's a comment here, and that this was in that Vulkan sample, that says set viewport dynamically. The reason why it says that, specifically dynamically, is because when we actually created the pipeline, we specified 2 different dynamic states, viewport and scissor, right? So you can actually have your viewport and scissor just set inside your pipeline kind of statically. Statically meaning that like it's just a constant value, it's set there and you can't change it. But if you put things like viewport and scissor into your dynamic state when you create your pipeline, then it means that when it's time to actually render and record these commands, you can set them dynamically. And that's just something that tends to be commonly done with viewport and scissor, because you might want to change it without having to rebuild the entire pipeline or have like a variant of the pipeline for a specific viewport. And of course, you can imagine this matters because we might resize the window and therefore these swap chain dimensions will change. So that's why it specifically says dynamically. Okay, so the next situation here is we really need a way to get the width and height of our window. Now, if we go to application, I'm sure we probably provide that, or maybe not, because again, Walnut is quite bare bones. So yeah, it doesn't really look like we have a width and height in here. We obviously do when we actually render the swap chain, and I think IMGUI is going to have that internally, which we could expose. And if we have a look at get main window data, you'll see that there actually is a width and height inside there. So I say we just use that for now. So if we have a look in init pipeline, you can see we actually retrieved this get main window data. So let's just go ahead and do that up the top. We'll just say auto main window data, or maybe we'll just call it WD for short. And then inside WD, we should be able to access the width and the height. Now in this case, they have to be cast to float. I might just clean this up quickly. Sorry, people who hate me for this, but I'm just gonna change it to a C-style cast. And then width and height, you can see a uint32ts. These are just ints. So if we wanted to, we could also cast that. I'm sure the conversion will be fine though. I don't know, will that give us a compiler warning if we don't cast it to an unsigned int? No, so I think that's fine, at least not at this warning level. All right, cool. Might just get rid of the comments because we don't really care too much. And then there's that command draw. And if you have a look at the command arguments here, then that 3 is obviously referring to the vertex count. And then that 1 is referring to the instance count. First vertex and first instance are also set to 0. That's like the index of that first vertex we want to start drawing from. Okay, that is in fact it. So technically speaking, if we run this, we actually should probably see a triangle on the screen. I don't know what will happen, obviously. We're probably going to get this far and it's not going to work, and then we're going to have to spend time debugging. The other thing we really need to make sure that actually works is even loading our shaders in the first place. So what I might do is the first thing I'm really going to do is I'm actually going to put a breakpoint over here to just verify like how far we get, basically, if we even get that far without Vulkan errors. Now the Vulkan validation layer is usually pretty good at pointing out errors and telling us why it happens. So that should just be printed to our console, because I think that's how it's set up inside this IMGUI/Walnut Vulkan application thing. So if we go to client layer real quick, we can see that we are running renderer init, and then obviously we want to actually render inside that onRender function. So really all we have to do is call render at the moment. That's really all there is to it. And the bind pipeline, vertex index buffers, which we don't have yet, and the draw call obviously happen just within this function, this one over here, every frame. So let's go ahead and hit F5, see what happens, see if this builds and links, and see if we hit our breakpoint there, and we can inspect the data to make sure that we create the pipeline successfully and load the shaders as well. Okay, so we have an exception here, access violation reading location, and you can see it's an offset of 14 bytes off of null. So that tells me that something is null, and we're obviously trying to read it at an offset of 14 bytes. So let's have a look. But also I'm curious, oh, this is inside load shader. Okay, I thought this was inside the pipeline. So yeah, most likely if we have a look at the buffer, I mean, the buffer size does seem to be 0, but the stream, if it opened the stream, that should have probably worked. Maybe one other thing I can do is let's just log this could not open file, and then we'll just do path.string. Actually don't know if we can just specify path like that. I also just realized we do have walnuts logging, don't we? So we could do like WL error could not open file, and then let's do path.string. I'll probably have to make sure that's included. Walnut core log, that probably should just be included everywhere. So one other thing we could add into here is probably stream good. So that's typically what I use. I don't know if open tells us that it could open the file successfully or not. Okay, so I guess it does open the file successfully, but the size just seems to be wrong, right? So the size somehow is 2 over here, which is definitely not correct. So the path is assets shaders bin basic. It's this one over here, which is like, 1,448 bytes. So what have we done wrong here? Okay, I've spotted the issue. So when we want to go to a particular place in the file, there are annoyingly 2 different versions of this seekg function. One of them just takes in a position, whereas one of them takes in that specific seek direction and an offset, right? So crucially, what we were doing is we were getting this basically like an enum that just says like, do we want the beginning of the file? Do we want the end of the file? And we were putting that the value of that enum as the actual position we want to seek to. If you look at these examples, you can see that it has like 0 as the first parameter and then this like iOS based thing. So that was definitely an easy error to miss. One other thing we could do is make this error checking a little bit cleaner by just doing if not stream. And I think that will either do good or is open. Anyway, it should work for our purposes. And then we can also say that if we fail to read the file, let's do the same thing. So I'm just putting in a little bit more error checking since that clearly didn't work. Could not read file, I'll say. And so we just need to put 0 and then that thing. So that is super annoying, but hey, it is what it is. So let's have a look now. Again, usually you would have this like in the core library or whatever of your game engine or framework, and then you wouldn't even have to worry about this. So I'm a little out of practice when it comes to raw C++ file reading. Okay, so let's see how big yeah, okay, that looks much better. We've got some stuff here. 1,448, which I believe was in fact the file size. So we are good. All right, let's continue on. Okay, so we get to VK destroy shader module. Let's have a look at our log. Doesn't look like we have anything in our log, which means we probably don't have any Vulkan validation errors, or at least these checks are not returning errors. I didn't really explain VK check, but basically what it does is we have a bunch of Vulkan functions like create graphics pipelines that returns VK result. And a VK result is just like an enum, which has a bunch of these things. If it returns 0, then everything's worked, right? VK success is 0. Everything else is basically an error, and it can tell us specifically what the error is. So all VK check does, and why we wrap it in that, is it just does a check to see the function that we run, what result it returns, and if that result is not 0, then it just prints it for us, and it converts that enum into an actual string so we can see it in the console as text. So that's what it does. And it's got this do while loop. I don't know if this is still, strictly speaking, the way to do it in modern C++, but the reason why this is here is just to wrap this in its own scope so that it can work with things like one-line if statements and some other syntactical things, especially if we still want to have that semicolon on the end there to make it look nice. Okay, so yeah, it looks like we have a graphics pipeline, right? This is set to a value. And remember, this isn't a pointer. Sorry for it being a bit faded, but this isn't a pointer. It's a handle, right? So that's why it might not look exactly like a memory address. It's not a pointer, it's a handle. And then we destroy the shader modules. So this is pretty good. Let's continue with this. And oh my goodness, we've done it. That was basically first try apart from the file loading. So guys, telling you, don't be scared of Vulkan. It's really not hard at all. I also completely, I thought the triangle was like this. I must not have looked at the vertices very closely. So if we did want to actually change the triangle to be like what I wanted it to be, if we go back to the vertex shader, here are the triangle positions. So 0.5, negative 0.5 is going to be, I keep drawing it like that. So this is clearly our triangle. So 0.5, negative 0.5 is going to be this index over here. Then we go up to 0.5, 0.5, and then we go negative x to get to here. So what we could do is we could just center this one over here by setting it to 0. This will allow us to just check our shader compilation pipeline, make sure everything is working. Let me rerun that, and that's the same result. That is weird. Oh, I'm modifying the wrong one. Let's make sure we're actually modifying the correct ones. I was modifying the ones inside the the example code. So we're just going to make sure that this vertex over here is in fact set to 0 to be centered. Then we have to run compile.bat, and then we just run our program. Oh, what's going on, man? That's that one. And then we find out that turns out our viewport's actually flipped, and going down is actually positive y. So that's not really usually the case. I think maybe that's set because of IMGUI. I suppose we can't exactly change that. One way to potentially flip that, I think, if I remember correctly, is if we go back to our renderer and we have our viewport set up. Maybe that's just normally how the swap chain works as well. So I think this we set to our height, and then the height becomes the kind of negative height. Okay, so we'll make the height of the viewport negative, and we'll make y the height of the viewport. So we're basically just reversing it, we're flipping it. And if we run this, we won't see anything because now like the winding order effectively has to be different, because by flipping the y-axis, we've basically flipped the necessary order of vertices in order for them to actually be like front face. We can verify this by going to our init pipeline function, and you can see here that we have a cull mode and it's set to back bit, and our front face is set to clockwise. I'm happy to keep that, but now those vertices have to be rearranged. So if we just set the cull mode to none for a second, we'll just verify that we can actually see our triangle, and there it is, right? It's been flipped, it's upside down. That's that vertex there. Let's keep culling the back face here, but then if we go into our vertex shader, we'll just make sure that this is actually done correctly. So our triangle positions, remember we have to go clockwise. So let's just start, for example, here, then we'll go up, then we'll go this way. So that up being at 0.5 is still correct. The first one though should be negative 0.5, negative 0.5 to be down there on the bottom. And then this one just has to be negative 0.5 on y and positive 0.5 on x. So we'll make it look like this. And that, once we compile, should in fact be what we were looking for. So that's good that we actually ended up playing with those vertices, because it showed me that we were upside down. Generally speaking, like our NDC, our normalized device coordinates, negative y is down. right? Whereas if we're talking about like application screen space, a lot of the time 0, 0 would actually be the top left. But when we do rendering in 3D space, I would say most of the industry has agreed that negative y should be down. And that makes sense when you think about things in 3D, right? You wouldn't really have a cube falling from the sky and the y is actually increasing, right? The y should be decreasing. So because of that, I just wanted to make sure that we are in fact in that right space. Okay, so now that we're Vulkan masters, how hard could it be to actually take this and do it properly? And by properly, I mean at the moment we're obviously we have these triangle positions here, but I would like to instead have a vertex buffer and an index buffer. Now we definitely don't need an index buffer for a triangle, and I might spend some time explaining what an index buffer even is, but we will need one for a cube. So our next step is going to be to take this data and move it to the CPU. At the moment, it's hard-coded inside our shader. I want it to live in a buffer that we actually create on our CPU, and then we upload it to our GPU to actually be read from by our shader there. So the first step for me is going to be to find an example that kind of does that. Looking through all the examples here, I don't really see anything like that. I mean, we've got like maybe the instancing example would be using like buffers. We've got a staging buffer here that we use for something. Okay, for our instance data, sure. We've got a uniform buffer in this example as well, which we could use. Actually, I just realized we probably don't have to look at this because the I'm GUI example has vertex and index buffers that it uses. So I might just keep this open, this instancing example. But if we have a look at our Vulkan implementation here, then inside render draw data, we did actually have create or resize buffer, which creates some buffers for us to use. And in this case, it's going to probably be a vertex buffer. Here's the usage. So the usage actually gets passed in. So in this case, you can see the usage is going to be a vertex buffer, and then we also create an index buffer. So I guess we might as well create both of these straight away, and then we'll test to make sure that that works. So we've got the VK allocate memory, create buffer. How does it get the memory? Oh, it probably gets mapped later, doesn't it? Yes. So we then use VK map memory and unmap memory. So this isn't exactly using a staging buffer, which is what you would like to do. And because of that, I'm sure the memory is going to be, well, it's going to have to be host visible, which I don't know how deep we want to get in this video because it's very easy to have this get away from us and dive into complexity. So let's just not use staging buffers today maybe. I'll quickly explain what that even means. So typically when we have a CPU and we have a GPU, they're obviously two completely separate devices and they also have their own kind of memory pools, right? So a CPU generally has the RAM that you have on your motherboard and a GPU generally has VRAM. It's a little bit more complicated than that because a GPU can also definitely access CPU memory. However, usually what we want is when we have some sort of data that really is only necessary to be seen on the GPU. So for example, in this case, we're just trying to render a cube, right? So that's clearly, once we kind of create that data on the CPU, we want to hand that over to the GPU, and then we want the GPU to store it in some form of memory that is going to be the most optimized and convenient for it to access every single frame to actually draw. And that kind of memory is usually called like a device local memory type. Whereas what we're using is something called host visible. Now, as that name might imply, and once you also understand that the CPU is the host and the GPU is the device, it means that it's a form of memory that's kind of visible to both, essentially. That's great if you want to keep writing to it from the CPU, but it also means that it may not be optimal for the GPU to actually access it, meaning it might just take longer to read from that memory. So optimally, for something like a 3D mesh, which might have some sort of CPU representation for things like physics or maybe CPU side frustum culling. When it comes to rendering, we essentially want that to be GPU only. So then the problem is, how do you get memory onto the GPU and have it be in that GPU only fast memory if you need to get it there from the CPU, but it's GPU only? So that's where staging buffers come in. You basically create two different buffers. One that is host visible that you can write to from the CPU, and then one that is GPU only. And so all of your data gets put into this host visible buffer, and then you run a GPU command using Vulkan. You create a command buffer, or you grab an existing command buffer, and you tell it to actually copy data from that host visible buffer into the GPU only buffer. And that operation happens essentially on the GPU. And then you can delete this and just have that super fast GPU only buffer. So that is what this concept of staging staging buffers is. I don't know if explaining it now was a good idea, but there you go. What we're going to do is we're going to skip that for now. We're just going to use this. It's going to be simpler. And then eventually we'll use staging buffers. They're not that complicated to set up, but I'm just trying to be brief. So this create or resize buffer function is essentially what we need. You can see by the way that ImGUI's method here is not to have that little VK check macro, but instead have a check VK result after every line of code, which I would say is definitely less clean, especially because we have to store all of these error codes or these VK results inside an actual variable like this. So I do like our way of doing things. Now create or resize buffer. Let's grab that function. We're going to put it into our renderer. I'll have it be over here at the bottom. And again, I'm just shoving everything into here because I'm trying to get this stuff up and running. If you would like to see me sort through this a little bit more and actually create proper like objects and renderer resources that we can use to make this a lot cleaner, definitely let me know. Okay, so I'm just going to have it return probably VK buffer. The thing is we also need device memory, maybe device size. So maybe let's come up here. We'll just create a struct. We'll call it buffer. We'll have it have these three things. So this is just our handle. This is like our buffer handle. This we can keep as buffer memory. And then buffer size is not a handle. This is just literally a buffer size. We could maybe have like a usage here. I don't know. We'll see. But anyway, this is the buffer that we're going to return, and then we'll call it create or resize buffer. Now, if we have a look at how this function is called in the first place, it's basically got this like new size that gets taken in here. So we have a current size, which could be 0, I guess. And then we have a new size, which it calculates. And obviously it checks here to see if either the buffer just doesn't exist or if that actual buffer size is less than what we need. Then it calls that create or resize buffer. I do kind of like that functionality actually. So let's just keep this as void. We'll pass in buffer and then we'll pass in this new size variable. And then we do also need a usage. So I have kept it very similar. I've just gotten rid of the verbose arguments, pack them into one. That's why I was saying maybe the usage should be there as well. Yeah, in fact, let's move the usage. We'll move the usage to being in here. And we can store this as like maxenum or something, just to be like an invalid value to initialize it with. Okay, so now if we have a look at this, why does it get BD? Probably just to get, Vulkan init info and to get the device, which we obviously don't need because we can grab the device over here. So let's sort of get rid of that. VK result and this whole error thing we really don't need. Now the buffer is going to be the buffer inside buffer. So sure, we can check to make sure, or rather we called it handle, to make sure that it's not null handle, and then we'll destroy it. So VK destroy buffer with obviously just device, buffer handle, and then the allocator. We're not using allocators, so we'll just have these be null pointer. We probably do want to use like VMA, which is a Vulkan memory allocator in the future. I totally forgot about that, to be completely honest. And then free memory will just be, what do we call it? Buffer memory. I think let's just call it memory because we're already inside that buffer context. Okay. Now we're doing like some alignment or whatever. We probably don't really need to do this. So I might just get rid of this and just pass in new size. We might revisit that if we need to. Buffer.usage will be the usage. And then finally over here, we can just do VK check. VK create buffer, device is device, buffer info we can keep here. Guess I'll make this look like more like our code. Buffer CI for buffer create info. The output buffer here is going to be buffer.handle, and that's, you can see we're passing that in by reference, so that's where we're going to be writing to as well. And the allocator will be null pointer. We don't need to check VK result because that's done in the VK check. Okay, so this is actually where we write in the buffer memory alignment based on those requirements. Again, I'll leave that out for now. We'll still get those buffer memory requirements since we have to allocate memory here. Again, this is really only necessary if we go with the alignment. We'll need that memory type index, which we'll get in a minute, and then we'll do device VK check. Buffer memory is going into buffer.memory, no allocator. Then we just need to bind the memory to the buffer, buffer.handle, buffer.memory, check the result here. And that's kind of it. We just need to write out that buffer size as well, which I might just call buffer.size like that. Okay, so we're just missing the memory type. So that's a pretty simple function. This is just something the renderer generally will have. I probably should just store this in a central location. For now, I'm just gonna really cheat here and just pop it into the top of this function because again, it's just super simple. All we need access to is that physical device though, instead of the regular VK device, which is like our logical device. So let's make sure we get our physical device, and then we'll just pass that in here, and we'll make sure we're in cubed get Vulkan info, and we'll set this to physical device. Okay, cool. Just a simple utility function. Okay, so now we really should be able to create or resize buffers. So let's go over here. We'll create our buffers. We'll call this buffer vertex buffer, and then we'll also have an index buffer. Then we'll go into our init function, let's do init buffers maybe. I'll create that function over here, and then we'll do create or resize buffer. So we've got 2 here. So for our vertex buffer, really the only thing we need to set is the usage. So let's do buffer usage vertex buffer bit. There's a bunch of potentially useful things here as well. Like you could, for example, have a vertex buffer that's also a storage buffer. It's accessible like through both, I guess, areas of the pipeline. Also, transfer source and destination is important if you want to use staging buffers. So you can actually use that like host visible buffer as a source and then the GPU only buffer as a destination. But for now, I think this is probably all we need. And we'll do the same for the index buffer, except as you can guess, it's going to be an index buffer bit. And then we just need to pass that in and then say what size we want it to be. So right about now would be a good time to actually create these vertices CPU side. So if I open up our vertex shader, this is it. I'm going to make this not be vec2s. I'm going to make them be vec3s, and we can actually use GLM for this. So GLM vec3, we'll just say vertex data. Sure, we can have 3 of them. I'm just going to add zeros to these for the Z component, and then also add an F because we're in C++. So these are going to be doubles if we don't add the F. The syntax also is going to be slightly different in C++ versus GLSL, and we'll make sure they're all vec3. So that's basically ported now into C++, and that is in fact our exact same data that we had before. We've just added those zeros, which really we've done because we want 3 component positions, we want 3D positions, because obviously for a cube we're going to need that. For a flat triangle we could have kept them as vec2s, but we're going to deal with vec3s. So how big is this now? So it's just going to be size of vertex data. It's a stack size array, so that should give us the correct size. Each float is 4 bytes, which means each vec3 is 12 bytes, which means we have 36 bytes of data here. So that's what that should give us. Now for an index buffer, this is going to be super simple, but really we'll use 32-bit indices here. I actually don't even know what, we'll see when we create it, what it gets set to, I guess. But if we do indices, we'll have 3 indices. This is literally just going to be 0, 1, 2. Again, no need to use an index buffer in this case, but we will anyway, because we're more interested in what Vulkan's doing than what we're doing. And we want to have that set up. So there we go. Could also obviously use 16-bit indices here, but we're going to use 32-bit indices. Okay, so, we are initializing buffers, is that right? We obviously need to actually put this memory into our buffers though. So we're creating the size here, but this actual data is never getting to the GPU. So if we have a look at what we had over here, inside the render draw data function, once those buffers did exist, we mapped the memory and then we did a mem copy into it. And then we flushed the mapped memory ranges to actually get the data onto the GPU, and then we're basically done. So this is really what we need to do. And you can see this happened for both the index and vertex buffer memory. So I guess let's kind of do this one line at a time. So first with the vertex buffer, once we've created it, we can do vk map memory. This can also have like a vk check. Usually I would create like an API so that we don't have to do this like using raw Vulkan code every time. But I guess we'll just do it with raw Vulkan code so you can kind of see how it works better. So the vertex buffer memory is going to be mvertexbuffer.memory. The vertex buffer size. Now in this case, again, we can just use size of vertex data since that's the data we're actually trying to get on there. So this is also like the range that we're basically trying to map here. We have some flags here and then a destination. So the way that mapping memory works is you basically create a C++ side pointer. So in this case, we're literally dealing with GLM vec3 here. So I could create a GLM vec3 pointer called like VB memory or something. I don't have to set it to anything because this, if we have a look at what this takes in, it takes in a pointer of a pointer because it wants us to give it the memory address of the pointer itself, since it's going to basically write into this variable a pointer to a block of memory that we can now write to. So it's like it's kind of mapped the memory on the GPU and now we have a pointer so we can write to it. Now, obviously, that's not how it works. We can't just map memory from the GPU. So what it will usually do, depending again on where that memory is stored, is it will just allocate a block of memory on the CPU that we can now freely write to. And then when we flush it, it'll copy it to the GPU. So that's kind of how that works. Now, you can see it's giving us an error because we also need that device here to do memory mapping. So let's grab this. I'll just put it at the top of the function. And now we just need to cast it to a void pointer. And we should have that memory mapped. So now we can do things like mem copy some data into it. Then we just need to make sure we flush it and we can unmap that memory. Not really sure if the flushing is strictly necessary. That will make it happen immediately, but I did think that once we unmap it, it might flush it, but I definitely don't remember without checking the documentation or the spec. So let's just keep it as this. So device. We have two memory ranges here that we're actually flushing. And then we have range B, those mapped memory ranges. So if I copy this, it makes sense because we actually have two here as well. So we can do them both at once, basically like batch them together. So it's a little bit faster. So here's our vertex buffer and index buffer memory. Whole size just means it'll just do the entire buffer, which is what we're trying to actually do here. And then unmap, we're going to do for both of these once they've been flushed. And that actually returns a void. Okay, cool. So that's got the vertex buffer there. Obviously, we still need to map the index buffer memory and we need to actually copy the data. So we can just do a normal mem copy. Quick little side note, because I had like a flashback to something that went horribly wrong back in the day. Make sure you don't use this function, because there's another function called memCompare, which actually compares if two bits of memory are identical or not. Very, very similar to memCopy. So just, I used that once and I was like, why isn't this working for like half the day, I think. So just, I don't know, this was back in junior Cherno days, but still, memcopy is obviously what you want. So the destination is going to be VB memory because we're copying into that. Yeah, that's another thing. With memcopy, the destination is always first, so just remember that as well. The source data is going to be the vertex data that we have, and then the size obviously is going to be the size of vertex data. Now, keep in mind, this obviously does not care about what type your data is, so the size is always in bytes. So that's that done. Now we have to kind of do the same thing with our index buffer memory. So we'll do our index buffer. We'll map that, obviously, the size of indices, and then we'll go into IB memory. It's a uint32t pointer, and then we can do a memcopy into IB memory from our indices, size of indices. Now our indices are down here, and we actually created the buffer there. So let's just make sure, well, we'll probably just I'll create these maybe up here, then I'll create both buffers. Maybe I'll actually even bring this down here so we can kind of group these a bit more. I think that might make more sense. Then we'll map the memory, and then we'll flush, and then we'll unmap. So I think that should work. Now, obviously one thing I could have done, especially for this simple example, is not created the memory here first and then memcopied it. I could have just written this data directly into the mapped memory, right? So that is an option, but I think this is showing a little bit more of like a real world example where you'd probably just have like a pointer coming in that you want to copy data from rather than directly creating the data here to be exactly in that mapped memory. Okay, I actually think that's pretty much it. We just now need to be able to access this on the GPU. Now, one thing I want to do quickly is test this. So if I just put a breakpoint here, I'm just going to run this and see whether or not this successfully ran. Okay, we didn't link successfully. So this create or resize buffer. Let's see what I did with that. So I just had it as a static void. So we obviously need that to be inside the renderer like that. Okay, so we didn't get anything in our log. And I mean, if we have a look at these things, they do look valid. So size of 12 for this and size of 48 for this. This is important because to get that size, you can see it gets written from these requirements, which are called through get buffer memory requirements. So if that didn't work, it wouldn't be here. And you can also note that even though we passed in size of vertex data, the actual size here is set to 48, not 36. So if we drag this all the way back here so we can step into here and have a look at new size, you can see new size is actually 36, but it aligned it for us. It created something of size 48. So that's just another kind of evidence of it working, I guess, correctly. So that's pretty cool. Now we need to be able to access those buffers inside our shader, or specifically we need to access the vertex buffers data per vertex inside our vertex shader, and the index buffer is just really used to determine like the way the vertices are actually rendered. So if we go back to our pipeline, over here is where we need to actually specify the fact that we even have like a vertex buffer that we're intending to use as part of our vertex shader stage here. So to have a look at how to do that, the simplest way is probably going to be, again, to refer to IMGUI, just because that's clearly where we were using these like vertex and index buffers in the first place. So if we have a look at the create pipeline function, maybe the create pipeline layout function, let's have a look at the layout function. So actually that just defines push constants in the descriptor set layout. So probably the create pipeline function over here, you can see we have a vertex input attribute description over here, as well as this vertex input binding description. And then we have this input state. All of this is pretty much going to be important. So let's just grab this and put it here. And then we're just going to use this as a reference. So at the moment, you can see from that hello triangle example that we base this off, the VK pipeline vertex input state create info, which is this, had nothing in it. But now we're going to need a bunch more. So let's copy and paste that in. We'll have our vertex input over here. That's going to need both a binding description and an attribute description, which is just these things over here. So let's grab those and we'll pop them up here. We've got triangle list over here as our topology, which is good. And I'm pretty sure we're not going to need really anything else. So let's close this and we'll focus on this over here. So the stride is going to be the stride between vertices, which in IMGUI's case, this is what's inside a vertex. So that's a really important thing. Again, I'm not really trying to teach like graphics programming in this video per se, but when you hear the word vertex, don't just think position, because it's not just like a position in 3D space. A vertex can really be any data associated with that particular piece of data, I guess. And yes, it is commonly a position. In fact, it's pretty much always a position, but it's not just a position. It's also like the texture coordinate, the UV. It might be a color. It'll be like a normal, a binormal, a tangent. It's a whole group of data that pertains to that particular vertex. So in our case, we do just have positions. So obviously the size of each vertex is just going to be that position, which is 3 floats. So we can just put size of GLM vec3. Input rate vertex is important because if we're using instance rendering, then it'll be per instance rather than per vertex, but we're not in this case, so it's just vertex. Attribute description is going to be the way that we actually access the different attributes, I guess, of every vertex. So you can see IMGUI is accessing the position, the UV, and the color, how we actually access that inside our vertex shader. Now, clearly we only have one thing that we want to access at the moment, which is just our position. So we can just make one of these, which means, of course, this doesn't have to be an array. But you know what? I'm actually going to keep it as an array because we will be expanding this soon, possibly in this video, depending on how ambitious I am. Now the offset is just going to be 0 because it's the first element. The type is going to be RGB32 S float. This might look weird because it looks like a color, but this is just the way that we basically specify what kind of data it is. So it's 3 32-bit floats and they're signed. So that's just the data type. And of course you can always go to this and find one that matches what it is you're supplying. There's our binding description as well that we're interested in. And then location is how we're going to access it inside our shader. So now would probably be a good place to jump back into our shader and be like, how do we even read from that now? So we have a layout location equals 0 out, but we're also going to make a layout location equals 0. So there's that 0 location in vec3 a underscore position. Now I usually write a for attribute. That's just a habit I have. So I'll keep it as that. And now this will be that input rate vertex per vertex 1 GLM vec3 that we're going to take in from our vertex buffer. So that's going to be a replacement obviously for these triangle positions. So let's get rid of the triangle positions. And instead of reading from them, we're going to read from a position. Now, because this is already supplied to us per vertex, we don't need to use this vertex ID. Not to mention a position isn't an array anyway, it's just a single vec3. So we can just do that. And of course, since it is a vec3, not a vec2, we can get rid of that 0.5. 0 should be a fine value as well. We can keep our triangle colors if we like for now, but we could have also packed that into a vertex. That might be worth demonstrating as well. Okay, and then continuing on here, I think that's pretty much it. So we just need to make sure that obviously we've added all of that to our vertex input. And I actually think, like, I don't know, obviously it's been a while since I did this kind of from scratch like I am now, but that might be enough. So let's just compile our shaders. And then we obviously need to go to our render function and actually render, make sure that we're binding those buffers. So somewhere here, we can do vk command bind buffer, or rather bind vertex buffers. So into our command buffer, that's just our command list. First binding, probably 0, binding count 1. The buffers are going to be, so you can see it wants a const pointer. So we'll do m vertex buffer.buffer. And then the device size offsets are just the offsets into there. So this will probably just be like 0. That's just a UN64T, but it wants it, you can see it wants it as a const pointer. That's why I had to make it like an L value like this. I mean, I didn't have to, I guess, but let's have something like that. And then what does this want exactly? This is handle. Okay, and that's how we bind vertex buffers. So let's do the same thing for our index buffers. We don't actually need an index buffer here. And in fact, let's not use the index buffer just yet, because if we keep everything as is, then we don't actually need to use an index buffer at all. So now we're actually binding that vertex buffer. I guess we just hit F5 and see what happens at this point. No idea. Okay, something wrong is happening because you can see my process memory is just growing. We're doing this like every frame or something. Okay, we're in create graphics pipelines. So that is definitely odd. I want to kind of go through maybe this section here just to make sure that worked. But otherwise we may have had a bad array size or something inside the create pipeline if this works. But no, this doesn't work. Okay, so we're in here somewhere apparently. And init buffers happens after init pipeline. Okay, that's probably bad. Well, let's see anyway what happens here. Okay, well that seems to run fine. So let's just hit 5. Yeah, okay. So somewhere in init pipeline, I think we've probably got an invalid size or something, or I haven't quite set something correctly up in here. So this is just size of vec3. This refers to binding description 0.binding. Oh, .binding. We didn't set that, did we? Okay, that is just set to 0, but I feel like I'd probably want to be explicit about that. Everything else kind of looks okay. Let's have a look at what could possibly go wrong in here. Okay. So our shader failed to compile. So it might be something to do with the file not being read correctly. I didn't notice that error earlier. Okay, so line 8. That's in here though. Okay, that does actually compile. Maybe I'm wrong. Okay, so that doesn't work. Okay, so when we hit VK create graphics pipelines, that's where it stops working. Like as in that's where it starts reading, I guess, an obscene amount of memory and probably allocating a bunch because it needs to copy it there or something. And yes, of course, that's over here. So what we've done here is... I should have noticed this. We obviously had 3 attributes originally from the code that I copied from IMGUI, and there's that 3 here. But now we only have 1. So what has unfortunately happened is it's still trying to read 3. And since it's trying to read 3, it's reading past the end of this into some other stack memory. And it must have like some huge number or whatever. And it's probably like, I need this much memory to store everything you've given me. So I'm just going to allocate a whole bunch. And that's why we saw that memory usage climbing. This wouldn't have happened if we just used STD arrays, by the way. So this is probably a good time to be like, you know what? Let's use an STD array for all of these things, basically. So in this case, we just have one element, but that's totally fine. We can still create an STD array like that with our binding description. And then we can have our attribute description like this as well. And the whole reason for this is because we can access the data easily, obviously, by just doing .data, but now we can actually do .size. And this does want a uint32t, so we'll have to cast it to a uint32t. But the point, obviously, is that now we can't really be wrong when it comes to the size of these things. So that being said, let's try again. Okay, so we'll see if we can get past that. Yep. And look, our triangle's here. Okay, so let's just make sure that worked. So over here in the C++ code, I mean, it seemed to, unless my shader didn't recompile or something. So let's offset this triangle a little bit. It doesn't really matter how we do this, obviously. I might just move one of the coordinates right into the corner. So this will be not quite in the corner, but it will be at the very leftmost part of the screen. So there you go, right? So you can see we're now actually taking that in from our CPU. Now with index buffers, let's use those quickly as well. So when we render and we have this bind vertex buffer, we'll also do bind index buffers, which will be index buffer dot handle. Now this is going to be probably a bunch of different parameters. I mean, that's not even a function, because it'll be bind index buffer, just one. You can have multiple vertex buffers, but not multiple index buffers. So let's see the parameters here. So we just have the buffer and the offset, I think, like that. Let's get rid of that because that's not a pointer anymore. And the offset is also not a pointer. The reason why this was a pointer was because they can be multiple, so you can have an array of them. So it has to take in a pointer so it can read that. And then the VK index type here is just going to be uint32. So that's very important that you get that right as well. So now we're binding the index buffer, which is going to do nothing unless we switch from command draw to draw indexed, right? So now we'll use that index buffer, which means we still need an index count, which is still 3. We need an instance count, which is 1. First index, vertex offset, and first instance are all going to be 0. So now with that code, let's see if we still get our triangle. And I probably should have reset the position. Oh, I did reset the position. There you go. So we're using index buffers now. Sweet. Let's expand this knowledge very quickly into drawing a square rather than just a triangle, because that will demonstrate index buffers actually being used. So in the init buffers function, how many vertices, or how many vertex positions in this case, do we actually need to draw a rectangle or a square? We need 4, because there are 4 corners to this. So even though this is 2 triangles and we're going to need 6 indices because we're drawing things in terms of triangles, we can only have 4 vertices. And you can see that demonstrates the usefulness of an index buffer because we don't need to duplicate our vertices, at least not yet. So to get this to work, and remember we are going clockwise. So let's start with -0.5, -0.5 as we are. But now instead of going to 0, we're going to stay at -0.5 x, but then go to +0.5 y. So this is going to be a bit of a rectangle, of course, not a square, because we're still in that -1 to 1 normalized device coordinate space. We'll go +0.5 and we'll stay at +0.5 y. And then finally, for the last one, we'll have +0.5 x and -0.5 y going down. We'll change this to be 4. I think everything should work just because we're using size of here, right? So these indices are now going to be 0, 1, 2. So 0, 1, 2 is our first triangle. So what have we made here? Actually, let's just verify. So that that, and that. So 0, 1, 2, and then we want 2, 3, 0 to make sure we're still in that clockwise fashion to draw this part. So 2, 3, 0, always good to visualize and verify. We'll make 6 indices here, of course. And that really is all we need. Like, that's it. We just need to make sure that when we render, we tell it to render 6 indices, and everything else I think should have just expanded to be correct. So over here inside our render function, let's just change this to be 6 instead of 3. And hopefully we'll see a rectangle. And there we go, we see a rectangle. Now I totally forgot about the colors array. So I don't even know how that's working, because in our shader, inside our vertex shader, we only define 3 colors, but this is actually gonna go out of bounds, right? So we should probably have 4 colors if we wanted this. Let's maybe make one of the corners pink here, and then that should be a little bit better. Let's compile that, we're all good. Let's run it. And then we have a pink corner over here and some nice interpolation going on. Okay, so now, the next step, since we're on a bit of a roll here, is let's make a 3D cube. Let's leave this 2D supposedly space and let's move things to 3D. So turning what we have here into a 3D cube is actually not very difficult at all, because what we have here is actually already in 3D. We can't really see it because it's a flat piece of geometry, and we're also not using any kind of like perspective projection or cameras or anything like that to make it look 3D. But if you recall, the vertices that we actually provided here are in fact 3-dimensional vertices. So really all we have to do here is expand these to actually form a cube. Now a cube of course has 6 faces, whereas this is just a single face made up of 2 triangles. And even though there are only 4 vertices, we use these indices to actually create 2 different triangles. Now, because going from this to a cube can be a little bit difficult to visualize, I prepared something for you in Blender. So what we have here is a very simple way that we can actually draw a cube. Now, what I want to do here is I'm going to first start by showing you the absolute minimum setup you need to basically render a cube. However, practically speaking, in the real world, it's a little bit of a useless cube because it doesn't have any information aside from the actual vertex positions. In order to more effectively render models in 3D space, we usually need more information, such as normals and texture coordinates, and what you're seeing here doesn't actually include that. However, I thought it would be good to start with this more simple example, and then we'll expand it to include normals as well. That way, we can actually get some nice shading on it, as you'll see. So let's have a look at what we have here. So this section over here, this is basically what we are drawing currently. We're just drawing these 2 triangles. They are a little bit stretched out and they do look like they're a rectangle inside our window. That's just because of our normalized device coordinates being from -1 to 1 in both the X and the Y axes, even though the window obviously is not square. But don't worry, that will be addressed later on in this video. I've indicated the vertex positions here, X, Y, and Z, as well as the index. So you can see here that if we were to draw this face, we would use 0, 1, 2 as the index with these vertex positions, and then 2, 3, 0, which is exactly what we're doing over here. Now, the one difference is the Z component here is just all 0, because for a flat quad like we're drawing here, a flat rectangle, it doesn't matter really too much what this is, as long as it's within that -1 to 1 clipping range, otherwise we just won't see it. However, since this has depth to it, I've put the vertices of this face at -0.5 Z, and then this face at +0.5 Z. So currently this is what we're drawing, and now to make up this cube, we just have to draw the remaining faces. Now there are only 8 unique vertex positions that make up a cube, as you can see here. We're basically just alternating between being -0.5 and +0.5 on each axis, depending on the face that we're working with. And the unique vertex positions are of course all of the corners of our cube, and we've got one hidden behind here. So now all we have to do is draw up these triangles with the vertices that we have available to us. So first and foremost, let's go ahead and add these additional vertices that make up this back face. So if I go back to my code, I'll just change these to be -0.5 as seen over here in this model. And then we just have the exact same ones, but they're +0.5 Z. Now, one other thing to quickly note here though, is that this side is now the positive X side, and this side is the negative X side. Whereas you can see over here that the second and the third index were positive X, which is what we have over here. But on this side, it's the first 2 that are positive X. So that's another change that you need to not forget. So let's go ahead and just grab all of these. I'm going to copy and paste all of these vertices. We'll change this to be 8. And then all I'm going to do is make all of the Z components of these vertices positive instead of negative, and then flip these as well. So we're dealing with positive X first, and then negative x. And that should match what we have over here, where we have positive x, negative y, positive z. Well, positive z is everywhere, so positive x, negative y, positive x, positive y. You can see positive x, negative y, positive x, positive y. So the hardest part really here is just to have this visualization down. I remember back in the day when I was doing this for probably the first time, I just had like pen and paper and I was trying to work all of this out. I really encourage you to do that. I've obviously just made this visualization to explain it better in this video, but if you don't understand this, or if you want to kind of understand it more deeply, just crack out the pen and paper, draw this for yourselves and try and figure it out. So now that we have all of the vertices written down, we now need to alternate the indices. Now, obviously we only have 8 total indices from 0 to 7 because we've only got 8 total vertices. We can't possibly have more indices than vertices because the indices are an index into this array over here. So we obviously can't exceed index 7. That's our last vertex. But to make up 6 faces, since each face uses 6 vertices, we have 6 times 6, which is 36. So we know we're going to need 36 total indices here. And now it's just all about looking at this and writing down the numbers that we need. And of course, making sure we are in fact following the winding order here, which is clockwise. So 0, 1, 2, 2, 3, 0 forms this first face. Let's keep going this way. So 3, 2, 5, 5, 4, 3. Let me just drop this down so we're kind of going per face here. So 3, 2, 5, 5, 4, 3. I do want to also note here quickly that you don't necessarily have to follow this exactly how I'm doing this, because you can see I've made the join here of the 2 triangles be like this, but you could have made it like this. And you also can start from any vertex really. Like I can do 5, 4, 3, 3, 2, 5. As long as I'm still creating those faces, the order doesn't really matter. But I'm going to follow kind of this convention that I've got here just so it's a little bit more sensical. So 4, 5, 6, 6, 7, 4, and then 7, 6, 1, 1, 0, 7. So those are all of our side faces. Now let's do the top face. So we have 1, 6, 5, 5, 2, 1. And then the bottom face is 7, 0, 3, 3, 4, 7. So this is our top, our bottom. I think this is our front, right, back, and side. Another thing that you have to watch out for is this back face. We're not looking at the front face. So this is the front face over here, 0, 1, 2, 2, 3, 0. We're not looking kind of through this and then seeing this and being like, ah, yes, this is like 7, 2, 5, 5, 4, 7, because that would in fact create the face correctly, but the face would be facing into the cube. Remember, the winding order clockwise defines what our front face is. So these triangles are really just facing a single direction, unless you turn culling off, and then you can kind of have two-sided triangles. But since we have back face culling turned on and we are culling the back face, only the front face is going to be visible. And what determines which of the 2 faces is the front face? The winding order. So you need to make sure that you go clockwise depending on which direction you want your face to face. Okay, so now that we have all of that done, we should technically see a cube. Now, are we going to? Well, initially probably not, because again, we're in this weird like -1 to 1 clipping space. We're not looking at the cube like side on, you know, from a camera or anything. We're just probably going to see the same thing we saw before, just this first face. However, let's just make sure that we can actually render this in the first place, because things have changed slightly. I mean, nothing really, I think, has changed apart from the size. So this is now 36, this is now 8. We're still using size of for all of these for the memory, so it should be okay. I think the only difference is inside the render function, we just need to make sure to render 36 indices instead of just 6. So let's try and run this and see what happens. Okay, we get nothing. And in fact, I should have expected us to get nothing, because what we did is we adjusted the vertices to be -0.5 and +0.5. So if you picture the camera being at 0, in fact, it's not really correct to say that the camera is here. But anyway, picture we're like at the origin kind of, and then we have these faces pointing this way and these faces pointing that way. We're obviously kind of inside the cube, and because we have backface culling off, we can't see anything. Now at this point, if you're trying to debug this, you've got a few options, and I'll give you some tips for debugging here, because I realize this is probably a lot to take in a single video. You may have issues, so let me give you some skills, some tools that you can use to actually try and debug this and see what's going on. I mean, first and foremost, just always make sure you have the console up, because we should be getting log messages in there if we have any Vulkan validation warnings or errors. And then the other thing that we can do is obviously change the culling, which I keep losing. So over here we have cull mode back bit, but if we just set cull mode to none, as we did a little bit earlier, then you can see we now see something, in fact. We just see this like black face here. So that's good. That means we are seeing some geometry. Now it's black because we're very, very much exceeding this like range that we have here. What I can do to potentially try and stop that is just mod this by the amount, which is 4. If I try and do that and just compile our shaders again, then at least we won't be exceeding that index. And now we see this, which is basically what we had before, but again, culling is off. So let's turn culling back on. So the other really useful debugging tool that I would recommend you take a look at is RenderDoc, which is a graphics debugging tool. Now, strictly speaking, I alternate a lot between RenderDoc and something called NVIDIA Nsight. In my experience, NVIDIA Nsight is much better. However, it is also more complicated. And for simple things, RenderDoc is both faster to use and easier to navigate and just makes a little bit more sense. NVIDIA Nsight also obviously only supports NVIDIA GPUs since it's debugging specifically NVIDIA GPUs, whereas RenderDoc works with pretty much everything. But in general, every GPU vendor has their own graphics debugging tools that you can use. RenderDoc is just an open source one that happens to work with pretty much everything, which is great. So now what I'm going to do is quickly show you how to use RenderDoc to see what's actually going on here, since we obviously can't see that at the moment. So the first thing we need to do when we open up RenderDoc is just fill in this executable path, working directory, and command line arguments. Now we do need the working directory set to load those shaders. We don't have any command line arguments, and we of course need the executable path. So if we just go over here to our output in Visual Studio, go up to the very top, you can see that what we just tried running was this binary here. So I can just copy that path right into the executable path. The working directory, when you run things through Visual Studio, is actually set according to the debugging and working directory, and you can see it's set to our project directory. So if I right click on the project, go open folder in File Explorer, this is what has that VCX proj file, which means that this path is what we're looking for. So let's paste that in as the working directory and hit launch. So now you can see I'm running this with an overlay that RenderDoc has provided, and I can press F12 or print screen to capture. So I'm going to press F12, it's captured something. I can now capture more frames if I want, or just close it, and it will automatically open up this capture. So now I can go through and see all of the different passes, everything that's going on. This isn't going to be a RenderDoc tutorial, and we will explore RenderDoc a little bit more in this series, I'm sure, but this is just a really nice way to see how everything is being rendered. So we have our color pass over here, and inside Event Browser, we have our VK command draw index with 36 indices, which is what we're using to actually render what we see on the screen here. So if I have this selected, I can go to Mesh Viewer, and this is really what I wanted to show, the fact that we actually have over here a cube, right? So we have successfully managed to create a cube, and this is the geometry that the GPU actually has at the moment, because that's what we're debugging. And here are all of our vertex positions that are in here. That is the vertex shader input. So that's like the vertices that are being fed in for this draw call. If we look at the output, we can see the resulting like projection that has happened to actually turn this into a 2D image on our screen. So this is just a really good way to make sure that everything is in fact working as you might expect, even though we haven't actually written any code that lets us visualize that properly. So definitely make sure that you have RenderDoc around. I'll have a link to it in the description below. Okay, so how can we actually zoom the camera out a little bit, maybe use a perspective projection so we can see a more realistic 3D representation of 3D things? Primarily, I'm talking about the vanishing point, meaning that things that are further away appear smaller. How do we get all of that up and running so that we can see our cube a little bit better? Well, that's where we need to start using some math. Now, the math that we need for this is really, really simple. And in fact, the harder part's going to be how to actually get that math onto the GPU in the first place. Of course, I don't want to write any like constant matrices in the shader. So instead, what we're going to do is add something called a push constant. Now, this is just going to allow us to get some data from the CPU to the GPU in probably the simplest way possible. In the future, we'll be using various buffers for this, uniform buffers, storage buffers, but at the moment, we're just going to use a push constant, which is a really cool kind of simple trick that you can use. I call it a trick because it's not really portable across every render API, and it's not something that really is used too much in the industry, at least back when I was working in the industry. Still kind of am, I'm just working my own stuff. But basically, when we render, which happens over here, after we like bind the pipeline and everything, we have the ability to run a Vulkan command here called VK command push constants. Now we're going to need the command buffer as usual. We're also going to need the pipeline layout, which we need to retrieve here from mpipeline layout. Then we're going to need the stage flags, meaning what shader stage we basically want to push data to. In this case, it's going to be say shader stage vertex bit, because we're going to push some data to actually, you know what, let's start with fragment bit. We'll just push a color and see if that works first. Offset, we'll keep it 0. I'll explain what that is later. And size, let's just do size of GLM vec4. And then of course we just have a const pointer here, const void pointer, which is just going to be a buffer containing our vec4 that we're about to create. So let's create a little color here. Let's make it pink. because magenta will be obviously very visible. All we're doing here is we're just testing whether or not we can actually get this data onto the GPU using this. So I'll provide a pointer to this memory over here. And that literally is it. Now, obviously our pipeline doesn't know that this exists, and clearly we're passing in the pipeline layout. So we need to tell our pipeline layout that, hey, by the way, we have a push constant in our fragment shader, and we need to add some code to our shader. But in terms of what we need to do at render time, that's it. So it's a really simple and it's a really quick way of getting some data onto the GPU. Huge limitation of push constants is that they are small, meaning you cannot push much data. Now, I believe the Vulkan spec says the minimum size is 128 bytes. And in reality, a lot of GPUs actually have it at 128. I think some NVIDIA GPUs, probably the higher end ones, have like 256 bytes or something like that. But either way, it's tiny, right? It's not like megabytes or anything. It's really not very big. And I would say that 128 bytes really is probably not enough, nowhere near enough, if you have any kind of complicated shader to just have all of the shader data that you need from the GPU, such as all the material data and like camera and scene data. You can't pack that into this small of a size. I mean, one matrix is going to be 64 bytes unless you start like removing rows that might be meaningless, or columns. But for this little test, this is going to be enough, of course, for us. And since the Vulkan spec says that it has to be a minimum of 128 bytes, if we use 128 bytes, of course, we'll be fine. So going into our pipeline, inside our pipeline layout create info, where we literally have nothing at the moment, let's go ahead and set these push constant ranges. So you can see this is an array of VK push constant range. So let's make an array of just one of these for now. And you can see that the push constant range has an offset, a size, and a stage flags. For now, we're just going to set our offset to 0. Our size is going to be what it was before, which is the size of a GLM vec4. And by what it was before, I mean what we wrote over here, size of GLM vec4. And then finally, the stage, as you can imagine, for us is going to be VK shader stage fragment bit, because we want the fragment shader to have it. So now we just set this to push constant ranges.data, and then we also need to set the size or the range count, which is going to be size of this array. Now again, that's the uint32t. So if we want to be good, we have to cast this to a uint32t, since this will be a size t, which is a 64-bit unsigned integer. Okay, cool. I'll sort this out a little bit. I'll just put this up the top. That way we have all of the actual layout info that we're setting down here. And finally, our shader just needs to know about this. So now if we go to our shader, into our fragment shader, instead of having this like input color that we have here, which we're using, let's write layout push constant, push underscore constant. We can optionally specify a layout here, such as standard 430. This just defines how things are like packed and if there's padding. We won't worry about this for this example. And then we write uniform and then some kind of identifier, but this is like an internal identifier. So I'll just write push constants or something. And then over here, we can basically define like the struct that is our push constant data. So it's just going to be a vec4 here called color. Now over here, we have the ability to basically specify a variable name. So if we wanted to address this via upushconstants.color rather than just color. So if we don't have a name here, then this is like the type name. It's not really the variable name. So we would just write color, which can make it look like you're not sure where it's coming from, which is why generally I give it a name such as u underscore push constants, u underscore for uniform because it's a uniform type. And there we have our color. So now if we compile our shaders and then we run this, maybe we'll see a pink cube. Maybe we'll get a Vulkan validation error. Maybe we'll see nothing. I turned backface culling off, didn't I? And there we go. Right? So easy, we have some data from the CPU to the GPU. So now, instead of just sending a color like that, let's see how we can use this inside the vertex shader to actually add a transformation to our GL position. So instead of having a vec4 color here, I'm gonna have two mat4s. Now, each mat4 is 64 bytes, as I mentioned, because it's made up of 16 floats. So I'm gonna have one called view projection and one called transform. So this together fills up that minimum requirement of 128 bytes. So that's all, folks. That's all of our push constants used up. Now, if we were actually trying to make something, we'd probably not send all of this data because, for example, this transform matrix has an entire like row at the bottom. So that's 4 floats. That's 16 bytes of data that's completely useless because it's always going to be 0, 0, 0, 1. But anyway, that's besides the point. We're going to use this for now. And so our view projection is going to be a projection matrix multiplied with the view matrix in that order, because we're using column major ordering. So view projection, the reason why it's written like this is because in something like DirectX where you have row major ordering, you'd actually do view times projection, not projection times view. Anyway, the projection matrix is going to define like what camera we're using and what lens is on it, if you will. And then the view matrix is just the transform of the camera. It's really the inverse transform of the camera. So if we move our camera back, the view matrix will kind of move everything forward to compensate for that. And that lets us have a camera, the concept of a camera in 3D space that's allowed to move around and orient itself somewhere. So remember, it's not the camera moving, we're actually moving the world around the camera, if that makes sense. And that's why this is an inverse transform. We call that the view matrix. And then finally, we have a transform, which you can see is separate from that view projection that defines our actual geometry. And the reason why it's usually separate is because a camera is set up basically like for each render pass, you could say. Like the main camera set up once for the entire frame, because that's your viewpoint, but then you're rendering multiple objects at different transforms, at different positions inside that 3D world. And so you need the transform to change, basically draw call to draw call, but the camera view projection does not. So again, in a more real setup, neither of these would be in push constants, but view projection would be in like some uniform buffer that's set like at the start of the frame and probably not updated until the start of the next frame. Whereas transforms, transforms are usually all packed for every object in the scene into just one kind of common large buffer and then indexed into there. But anyway, I'm getting a little bit ahead of myself, so let's continue. So what we're going to do here is we're going to keep this GL position being vec4 A position, but we're going to multiply view projection with the transform and then that vec4. So this is what our line of code looks like now. I guess I'll drop this down a little bit so you can see what's happening over here. So now back in our C++ code, we obviously have to adjust everything to make up for that. So push constant ranges are now going to be the size of a mat4 times 2, which is 128 bytes. We're going to change this to be in the vertex shader, no offset, meaning we are starting kind of from the beginning. And then over here inside our render function, we're going to change this to be vertex bit as well. The size is going to be mat4 times 2. We'll change this to be called push constants. And what I'm going to do is just create an array of 2 mat4s, which we're about to set up. So we have GLM here, which is great. GLM's a math library. So for the first matrix, that's going to be our view projection matrix. You know what? Let's change this a little bit just so it's more clear. So let's do struct, and I'm going to regret putting this exactly here, but whatever. We'll do push constants, GLM mat4 view proj or view projection and transform. And we're going to call this push constants. And then that's what's going to go in here. So here we can just do size of push constants, not times 2. And then over here, yeah, we still just give it the memory of push constants. And this, instead of just having an array of 2 matrices, actually gives them names, which is a little bit more clear. So view projection, we're going to set this to be a GLM perspective. Now we need to include GLM, GTC. So quick little tip about GLM, there's 2 different folders here under GLM, GTC and GTX. X is like the experimental stuff, but pretty sure most of the Quaternion library is actually still in there. So it's important. I've actually looked at what GLM's updated recently, but anyway, GTC is like the core stuff. And then under here, we're going to have a few different useful things like matrix transform, which I think is possibly the one that has that in there, or at least it includes other header files which has that perspective function defined. So now you can see we have perspective. Perspective FOV is also another good function. That just lets us provide a field of view in radians. So let's do that. Let's use this. We'll do GLM radians, and then I'll use 45 degrees as our field of view. Then we have a width and a height. Now, the reason why we have this is just for the aspect ratio, right? So it needs to know the aspect ratio of the window, and that's going to help with making the cube not be a rectangle, right? So I think we have WD height and width here. So let's actually grab this. I've got an idea. Let's grab this. Let's pop it up here, and we'll call it float viewport width and viewport height, just because these are already cast into floats. And then we can just use viewport width over here, negative viewport height and viewport height. Okay, so now we can just write viewport width, viewport height, Z near and far. Don't worry about this too much. We'll set it to 0.1 and let's just say 1000. That's going to be important for our depth buffer and lots of other things, but we're not going to talk about it now. So that is our perspective projection. So now what we have to do is move the camera somewhere. So what I've shown you here is just the projection part of our view projection matrix. So now we have to take this and multiply it by the view matrix. Now to create this and to make it more clear, what I'm going to do is I'm going to create a mat4 here. And by the way, I always forget which way Z is. Like if positive Z is like back or front, it depends on our setup. So we might have to play around with these numbers a bit, but let's create a camera transform. So this isn't a view matrix yet, it's just a camera transform. And what I want to do is I'm going to translate this camera. We can just start off with an identity matrix here. We'll translate this backwards. We'll keep it at the origin. We're not going to worry about rotation or anything just yet. And I'm just going to go maybe like 3 units back here. So I say 3 units, and it's up to you to define what your units are. We're going to be using meters for this game, I imagine. So you can picture this as 3 meters. And remember, these units are only really important in relation to other things, right? So the reason why we define units in the first place is so that we can make objects of relative sizes to each other. If you don't have a unit set up like this, then you can't really control that. So now to go from this camera transform to an actual view matrix, we just need to invert this matrix. So we'll do GLM inverse camera transform. Now, in this case, we clearly could have just written +3, like instead of -3, and not done the inversion, especially because inverting a matrix is not really that much of a cheap operation. It's quite expensive. But since we'll be adding like rotation and other stuff to this in the future, this is going to make more sense. Okay, so now what we'll do is just set up this transform. Right? So we'll do this, and this is the transform of our cube. So what I'll do is I'm just going to keep it at an identity matrix for now, but we're going to be able to move our cube around if we want independently from the camera, which is great, especially if we want to render multiple cubes. Okay. That should be good. Let's compile our shaders because I don't think we did that. Make sure that's all good. And let's try running it and see what happens. Okay, so we get nothing. 2 possible reasons for that. It's probably me just not knowing which way forward is, as usual. Okay, and there we go. So we see a red cube here. Why is it red? Oh, because we didn't update our fragment shader to not use it. So let's go back to using this in color instead of, and that's a vec3. So we'll do vec4 in color and 1, because obviously we removed this push constant, so we don't have that anymore. Okay, let's compile, let's run. And there we have a very weird looking cube. Now, the other thing that I think we're not doing whatsoever that has become apparent now is depth testing. However, before we look at that, let's see if we can get this cube rotating a little bit. So if I go back to my renderer, at the moment, these push constants are here. And I did share my regret of putting them into here because we're going to want to control them outside of this render function. So let's grab these push constants. Let's put them over here. I'll call this m_push constants. So now they're gone. We're going to use m push constants everywhere. And this is good because now we can set this like outside of the render function, obviously, and we have persistent storage for this because it's no longer a local variable. So what I might do is I might actually set up kind of a transform or whatever for our cube out here. So we'll have glm vec3 cube position, which I'll just initialize to 0, and cube rotation. And if we go back over here, the transform now is going to be of the cube. We're going to do glm translate. We'll just pass in an identity matrix and then that cube position. And then to go from our vec3 rotation, which is just an Euler angle representation, we have to include GTX, and then there's an Euler angles header file over here. And we can do GLM Euler angles. There's XYZ, or YXZ. There's lots of these ones because a lot of times we might have like your pitch roll instead of like pitch your roll. But anyway, we'll just do the Euler angle XYZ here, and we'll just do cube rotation. I guess it wants X, Y, and Z. Okay, so hopefully that will work. The only other thing is that I would like to see these in degrees. So let's cast them all to radians. I say cast, but we're just converting them from degrees to radians because we of course would rather see degrees. So cube rotation and position are now things that we can actually set using IMGUI. However, that's not inside the render class. So what I'm going to do is inside here, I'm going to make a new function called render UI. And then from our client layer under the on UI render function, maybe after the demo window, I don't know why we're still showing that. Let's go ahead and do renderer render UI. So now we're calling this, let's begin a new IMGUI window. We'll just call this like controls or something for now. And then let's just have 2 drag float 3s. This will be our position, which will be GLM value pointer. GLM value pointer, by the way, just lets us basically get like the pointer of the underlying memory of really any GLM type. It's super useful. It's under the type pointer header file. Of course, in this case, we could have just gotten the memory address of the first component because they're going to be packed together, but this is a little bit more of like a safer way to do this, especially across all types. So this is our cube position, and then we have our cube rotation as well. So let's launch this and see what happens. A whole bunch of errors. Awesome. So GLM over here wasn't used, or rather wasn't included. So, I mean, they're just definitions. So we could probably just include GLM. Let's see if that compiles. Okay, that looks good. Let's build the whole thing and run it. All right, cool. So you can see now we have the controls here. And if I move this, our cube actually moves, and we can move it in all of the axes. Now, the rotation of the cube as well is going to, well, predictably rotate our cube. Now, let me quickly just change the amount that these values get incremented. So an additional parameter of drag float 3 is the speed that we want. So maybe like 0.05 or something is what I'll use just to make it a little bit smoother and easier to manipulate. We could have used sliders as well. There's slider float 3 instead of drag float, but usually I end up using drag float. So now you can see it's like a lot smoother and we can rotate everything. Okay, so now that we can rotate all of this, we can have a look at why some faces are sort of in front of others, and it kind of looks weird. But if you have a good eye here, you might see that it's not just that some faces look like they're in front of other faces, it actually looks like our cube is inside out, right? So it looks like these are the faces that we're looking at, and they're all obviously pointing inwards, and that's why we can see them. And if we have a look at like this top face that doesn't exist at the moment, if I rotate this, you can see it appears as soon as I go under it. So basically our faces are facing the wrong way. But how can this be? Because clearly we've got our front face set to clockwise, and the way that we define those vertices seems like they were in fact clockwise over here. So what's gone wrong? What's gone wrong is I've messed up which way far and near is. So I always picture going away from the camera as going positive Z, but it's actually negative Z. And we proved this when we actually set up our camera transform. So you can see that if we're looking at our world top down and the cube is over here in the middle and our camera is here, you would picture this as going back in the world so that we can obviously see our cube. But we went positive 3. And I mentioned, of course, back then that, I've messed up the orientation, I guess, of that Z axis. And since I've messed up that orientation, that means that this Z is not actually negative because it's closer, right? This is supposed to be a positive Z, and that's supposed to be negative Z. So in order to fix this the correct way, we'd have to go down here to our vertices and simply flip the Zs. So this becomes positive and this becomes negative. And now if we run this code, then you can see we have a cube that looks like it is in fact the right way, facing, I guess, the right way. The faces are not facing inward, they're facing outward. So that looks pretty good. Now, this is all great, and you can see that we have successfully drawn a cube and it looks pretty good, but the critical information that we're missing here that we definitely need are things called normals. So normals are just vectors that are perpendicular to a face. So this is a face, right? Which way is the face facing? This way. And don't forget that a face is actually made up of 2 triangles. So which ways are these triangles facing? Well, they're facing that way, which could be, I don't know, like the positive X axis or something like that. In which case, a vector going the positive X axis would be 1, 0, 0. So what does that look like? Well, here is our unit cube with normals, which I prepared earlier. So if we have a look at this, we have 0, 1, 2, 3 as we have, but I've added these normals over here. Now, whilst we had only 8 unique vertices before, because we do in fact still have 8 unique vertex positions, now things get more complicated, because even though this one position is used 3 times for this face, and for this face, and we can reuse it using indices, these 3 faces have different normals, right? This face faces this way, meaning these 2 triangles, and well, the triangle using this vertex is this triangle up here. That faces that way. This faces this way, and this faces this way. And you can see I've written the normals over here. So this faces -1 on X, this faces 1 on Y, and this faces -1 on Z, although now it's going to be +1. So what that means is that we now need 3 of these vertices. Even though it has the same position, it has 3 different normals. One with this normal, one with this normal, and one with this normal. So because this video is already, I'm pretty sure, long enough and probably a lot to take in, I'm gonna leave this as an exercise for you to do for homework between this and the next video. I'll be implementing this, adding some normals to our cube and adding some lighting as well, but I think it would be a great exercise for you to try and do this yourselves, especially because this cube that I've created in Blender should be a pretty good visual aid. I'll just let you soak it in for a bit. And you can see, by the way, that the indices go all the way up to 23 here. So we're going to need 24 unique vertices now, even though we have those 8 positions and some of them do get duplicated. So go ahead and add in all of these normals. You'll have to also change your pipeline so that it includes 2 attributes now, and you'll have to take them into the shader as well if you want to do some lighting. So go ahead and try and implement that yourselves. If you want to discuss this, and in fact this entire series, I've made a channel on Discord as well where you can talk about all of this. Now the last thing I would like to do here today today is actually connect to our server and basically have these cubes instead of those squares that we were seeing. Okay, so our server is now up and running. So if I connect to it, then we should see our square that we actually created last time. And here it is being rendered on top of everything. So I'd like to replace this now with cubes. So what do we need to do for that? Well, first of all, instead of render, let's introduce a new function called render cube into our renderer. And all I'm going to do here is realistically just have like a position for our cube. So let me take this in as a const reference. This is just a cube being rendered at a particular position. We're not going to worry about like colors or anything like that. They'll just be the same color, but we will render them at 2 different positions. So what I'm going to do is I'm going to grab everything that we have inside the render function here. I'm going to copy it into here. Most of this stuff is going to stay exactly the same, except the transform currently uses mCube position, but I just wanted to use position. That's it. Everything else is going to stay exactly the same. Now, I want to quickly point out that the only actual thing we need to do to render 2 cubes is this over here. We need to push the constant, which contains the transform, and actually do the draw call. Everything else here, including setting this viewport, binding the vertex buffers, index buffers, binding the pipeline, all of that you should really only just do once to kind of set up your render pass, and then you should just have your draw calls, because we're doing a lot of stuff here needlessly if we're going to run this multiple times, which we're about to do. Now, what I actually want to control here though, rather than cube position and rotation, is basically the same thing, but I just want to have some controls for our camera. So let's do camera position and rotation, and then under render UI, let's add in camera position and rotation. We'll be controlling our cubes externally, so I'll comment this out for now. And then inside render cube, where we set up our camera transform, which is another thing that we shouldn't be doing per cube, we're going to use GLM translate with M camera position, and then multiply it with this Euler angle that we have, but for camera rotation, X, Y, and Z. So this will probably remain at 0. Our cubes can't really rotate at the moment, so we don't really have to worry about this at all. Okay, cool. So we can control our camera now. I think we had it as 030 initially, so I'll set it to that. Rotation, we can keep it 0. This is inside the render cube function, and the render function, which contains all that other code, is going to do nothing, because we're going to go to client layer, and instead of running client layer on render and running render, we're instead going to render cube potentially multiple times. So if we go to on UI render, this is where we go through all of our players, including ourselves, and render them. So let me just grab this code that does all the rendering, in fact, including our connection status, because we only want to do that if we're connected. And then just instead of calling draw rectangle, let's call render cube, and we'll render cube at, in this case, the player position. We don't need to worry about the size or anything like that. This is a vec2. So we'll go ahead and just add, let's keep the Y at 0, or in fact, maybe 0.5 if we want to be correct, because the center point of the cube is the origin. So if we want it to be kind of on top of the game world, on top of the floor plane, not that we even have one, we would set it to 0.5. So let's just do that, sure. And then player position.y will be our Z component. Let's copy this now, and then do the same thing for this draw rectangle that is for the other players. So we'll do data position X and Y, and then we'll no longer do draw rectangle. I'm also going to just disable this branch here so that we don't render our squares on top of everything by just setting this to false. And so now, technically speaking, we should render everything, all of the players, as long as we are actually connected and we can see them. So let's go back to our server. I'm just going to stop our server and restart it, because otherwise we'll have players that have already left already there. And then let's go back into our client. Let's try and run this. We've got our camera controls over here, which we'll adjust in a minute. We'll connect to the server over here. Now, I think we did actually connect, but we're still showing the UI because unfortunately I did this if false thing and did not notice that that means that this has to run. So let's actually keep this here, but I'm just gonna do an if false for this section just to disable it, at least for now. We could probably just remove it, to be honest, but I'll keep it here. Let's restart this. Let's connect to our server. Okay, we're in apparently. We can't see anything. Again, probably because of that camera. Oh, a huge thing that I just realized though, that it definitely isn't gonna work, is the fact that our game world used to be in terms of pixels, but now it's not. So if we have a look at where we're rendering this, the position is like 50, which is huge, right? So what I wanna do is inside render cube, I'm actually going to grab this position and I wanna divide it by some kind of factor, like a scale factor basically, because our cubes are only 1 by 1, but this world is going to be giant. So let's maybe call this translation, and then we'll do position, and then we'll divide it by our cube scale or something. So we'll add a cube scale. I'll set this to like 0.1 or something for now. I'm going to add it to my IMGUI controls because I might want to manipulate it. So I'll just call it scale, memory address of cube scale, and yeah, sure, we can have it maybe 0.005 or something, but we can always type in a number there. We don't have to actually drag it. And then inside render cube, we'll just make sure that instead of using this position, we'll use our translation. Translation and position are kind of synonymous in this context, but anyway. Okay, let's try it again. Again, restarting our server. We'll connect to our server. Okay, and now let's have a look. So we can obviously change where the camera is, but because we're rendering this top down as well, this is going to affect stuff. Okay, so silly me, divided instead of multiplied. So we actually ended up increasing our scale massively. So let's make sure that we multiply with our scale. Okay, another dumb thing I did was I set the camera position for some reason on Y instead of Z to be 3. I don't know how I managed that. Okay, so now if we connect to the server, if we zoom out a little bit, we move ourselves back, we can actually see our cube. Now, if I wanted to be top down here, then I could lift myself up a little bit and then rotate on the x-axis, like say minus 90 degrees. And then if I just increase this, then you can see, if I go back to the origin, I have a cube here, top down. Let's maybe zoom in a little bit, and I can of course move it with the WASD keys. But now the magic is going to start, because if I launch another instance of this, so let's go to our cubed client, start a new instance and hit connect. On this first one, I can now see 2 different cubes, and we are in fact playing in multiplayer. Now, we would have to take these camera controls here and make them similar to this if we wanted to see the exact same view, of course. But you can see we're in that same like multiplayer setup that we had, except we are now rendering everything in 3D. And that of course means we can adjust this however we see fit. And hopefully you can start seeing that we're getting a little bit of 3D squared, aka cubed, up and running. So ladies and gentlemen, that is going to be it for today. I think we've covered a lot of stuff today. This was quite a crash course on 3D rendering as well in Vulkan. If you're looking to learn, then definitely make sure that you have a go at that exercise that I mentioned with adding normals to these cubes, because then you can actually get some nice lighting up and running, and hopefully you'll be able to start to see this game come to life. Now that you know how to render multiple objects, another thing that you might try to do is actually add like a ground plane to all of this. So that's even easier than a cube because it's just one face. Make sure it's obviously facing up and render it at the origin of the world, and you should see a nice ground plane for all of our cubes to be on. If you enjoyed this video, please as always don't forget to hit the like button. You can support my channel and this series by going to patreon.com/thecherno, and I will see you next time. Goodbye.